This question is about specific latent heat and specific heat capacity. The first part of the question says, explain what is meant by specific latent heat of fusion. In order to answer this question, we need to understand the two parts of the definition. Firstly, what the specific latent heat means, and what a specific latent heat of fusion specifically means. So firstly, the specific latent heat is the energy required to change the state of 1 kilogram of a substance without changing its temperature. This second part of the definition is important because without it, we would be taking into account more than the energy required just to overcome the interactions between the particles. Instead, we would also be including some energy used to heat it up instead. The fusion part describes a phase change from solid to liquid. Note that it has to be this way around because in our definition of specific latent heat, we said that it's the energy required to change the state. What we're doing when we change the state from solid to liquid is we're breaking bonds, thus making the particles in the substance more free to move, whatever they are. What we're doing when we change the state from solid to liquid is we're overcoming interactions between the particles. This means that when the interactions are overcome, the particles are more free to move. This denotes the transition from solid to liquid. Therefore, we have to put energy in to overcome those interactions. Thus, our answer is the energy required to change the state of 1 kilogram of a substance from solid to liquid without changing its temperature. In this question, we got 1 mark for saying the first part of the definition, that it's the energy required to change the state of 1 kilogram of a substance from solid to liquid. And we got 1 mark for saying without changing its temperature. The next part of the question says, Figure 1 shows how the temperature of the water is maintained in a hot tub. The hot tub system has a volume of 4.5 meters cubed and is filled with water at a temperature of 28 degrees Celsius. The heater transfers thermal energy to the water at a rate of 2.7 kilowatts, while a pump circulates the water. Assume that no heat is transferred to the surroundings. Using this information, the question wants us to calculate the rise in water temperature that the heater could produce in 1 hour. And we've been given the density of water, and we've been given the specific heat capacity of water. In order to do this question, we need to use the fact that energy is conserved. So all the energy from the heater goes into the water. We are allowed to assume that all the energy stays in the water because we're told that the water is perfectly insulated from the surroundings. Since we're told that the heater has a certain power and that it transfers energy to the water over a period of time, in this case 1 hour, it is suggestive of the fact that we need to use the power of the heater, is equal to P, is equal to the energy transferred to the heater divided by the time over which that energy is transferred. Therefore, we can rearrange this equation to get the energy transferred, E, as equal to P times by T. Since we have been told that we're looking for a rise in the water temperature, it is also helpful to consider an equation that contains a rise in temperature, specifically that the energy transferred to a substance is given by the mass of that substance multiplied by the specific heat capacity of that substance, C, multiplied by delta theta, the temperature change of that substance. Therefore, due to conservation of energy, we can say that the energy transferred is equal to the energy gained by the water, like so. So these two are equivalent. Therefore, we have that PT, the power of the heater multiplied by the time that that power is applied for, is equal to M times C times delta theta. So far, we know that we have the time as 1 hour, we have the power as 2.7 kilowatts, and we have the specific heat capacity C. However, at this point, we don't know the mass. However, we can use the fact that we have the volume and the density and look for an equation that contains those two things and the mass. Specifically, we can write that the density of the water is given by rho is equal to m divided by v, m being the mass and v being the volume. Therefore, rearranging, we can write m is equal to rho times by v. So therefore, we can calculate that as being 1000 from the density, which is up here, multiplied by the volume, v, times 4.5. So this is 4,500. Now we can rearrange for the temperature difference delta theta. Specifically, we can write by dividing both sides of the equation for delta theta, dividing both sides by mc, we find that delta theta is equal to pt divided by mc. So substituting numbers in for this, we can do that the power is equal to 2.7 times 10 to the 3. That's from converting kilowatts to watts. So because kilo corresponds to the power of 10 to the 3, we have to include that. Then we have that the time is 1 hour, so we need to convert 1 hour into seconds to use our equation in SI units. Therefore, we have to multiply by 1 hour multiplied by 60 to convert hours to minutes, and by 60 again, which will give you 60 squared, to do minutes to seconds. So that's the conversion of hour to seconds. Then, on the bottom of this equation, we have the mass, as we worked out before, as 4,500. That would be in kilograms. And then we can multiply that by the specific heat capacity, 4,200, like so. This gets us a value of 0.5142857 Kelvin, which is approximately equal to 0.51 Kelvin. Therefore, our answer is just that. The reason we've chosen to round to two significant figures here is because the precision of the data we've been given is all to two significant figures. Whenever writing answers like this, you should give your answer to the lowest degree of precision of any piece of data given in the question. In this question, we got 1 mark for trying to substitute into delta theta is equal to pt divided by mc, when using the m is rho times v. We get 1 mark for getting this substitution entirely correct, and we get 1 mark for our correct final answer. The last part of the question says, the pump can circulate the water at different speeds. When working at higher speeds, the rise in temperature is greater. Explain why. Again, assume that no heat is transferred to the surroundings. In order to answer this question, it is helpful to consider what the pump is actually doing to pump the water around the pipes and through the heater. Specifically, we have that water is being moved from one location to another, and a force is being applied. Therefore, the pump is doing work on the water, since a force is being applied on it over a distance. However, if the pump continued to just do work on the water repeatedly, without any of that energy being dissipated, then the water would just move faster and faster, which we know is unphysical. In reality, that work will be dissipated as thermal energy in the water. Therefore, what we have is that as the pump moves faster, it's doing work more quickly on the water, and this work, which turns into kinetic energy of the water, is soon dissipated as kinetic energy of the water molecules, and so the mean kinetic energy of the water molecules rises. This leads to the temperature rising. Therefore, the work has been dissipated as thermal energy. If the pump moves faster, then more water has work done on it, and so more work is done in total. Therefore, this temperature rise is higher. Thus, our answer is that the pump circulating water forces it to move, doing work upon the water. This work is dissipated as thermal energy as the mean kinetic energy of the molecules in the water rises. Thus, the pump doing more work in a shorter amount of time In this question, we got 1 mark for saying that work is done upon the water. We got 1 mark for saying that this is converted to thermal energy. We could have also gained that mark by saying that it raises the mean kinetic energy of the water molecules, which is related to their temperature. This question is about electric fields. The question says, define the electric field strength at a point in an electric field. In order to answer this question, we use the definition of the electric field, which is that it is the force per unit charge acting on a small positive test charge at that point. The fact that we include the small positive test charge is important because the idea is that the small positive test charge has a charge small compared to the charges involved that generate the field. This means that it does not disturb the fields created by the other larger charges. The reason that the force is per unit charge is because the size of the electric force varies with the size of the charge that it is acting upon. More charged particles feel a larger electric force. Therefore, it makes sense to define it in terms of the force per unit charge. In this question, we got 1 mark for saying that it was the force per unit charge, and we got 1 mark for saying that it acts on a positive test charge. So the keyword being positive. This is important because if it was a negative test charge, then it would mean that all the electric field lines would be the other way around. The next part of the question says, Figure 2 shows a point charge of plus 46 microcoulombs placed 120 millimeters from a point charge Q of unknown charge. Point P is on the line joining the charges at a distance 66 millimeters from the charge Q. The resultant electric field strength at position P is 0. Calculate the charge Q. In order to answer this question, since we are dealing with electric fields from point charges, it makes sense to use the equation for the electric field of a point charge of magnitude Q. Specifically, the E, the electric field strength, is equal to Q divided by 4 pi epsilon naught r squared, where r is the distance from the charge Q. Next, we must note that the charge Q must be positive. This is because for there to be a region where the resultant electric field strength is 0, it means that I must have repulsion that would push a charge placed at P away from the charge Q and away from the 46 microcoulomb charge. Therefore, that can only happen if both the charges Q and plus 46 microcoulombs have the same sign, i.e. in this case they'd both be positive. In order to make progress then, we need to consider the resultant electric field strength, since we're told that this is 0. In order to make the notation easier, I will call the 46 microcoulomb charge Q1. I'll call 120 millimeters D, and I'll call 60 millimeters R. So then, using this, the resultant electric field strength at position P is given by Q divided by 4 pi epsilon naught multiplied by R squared. So this is R, the distance between Q and the point P, minus Q1 divided by 4 pi epsilon naught, and then the distance between Q1 and point P all squared. So that's D minus R. This distance here is D minus R, which is going to be equal to 54 millimeters, like so. And that's equal to 0. The reason that we subtracted here is because we know now that we've figured out that Q is a positive charge, it means that the electric field from Q is pushing would cause a force that pushes a test charge at P to the right, and the electric field from Q1, the 46 microcoulomb charge, would produce an electric field that wants to repel a positive charge, so will push it to the left. Therefore, these two fields are in opposite directions, and so we must subtract their magnitudes, like so. So we can now rearrange this equation using the fact that 4 pi epsilon naught appears in both terms and 0 is on the other side. So we may multiply both sides by 4 pi epsilon naught, which cancels it. And then we may move q1 and d minus r all squared to the other side. So we have q divided by r squared is equal to q1 divided by d minus r all squared. Then we can rearrange by multiplying both sides by r squared and simplifying to put everything inside a bracket to save us work when we enter this into the calculator, as q is equal to q1 times r divided by d minus r all squared. Finally, we can substitute numbers in, giving q is equal to q1, 46, times 10 to the minus 6. So that comes from the micro in microcoulombs, so that's converting microcoulombs to coulombs. And then for the distances, because everything is in millimeters and I'm dividing the two by each other, the unit cancels. Specifically, we have r is 66 millimeters and d minus r is 54 millimeters, like I annotated above, all squared. So in this case, the millimeters will cancel each other. This will lead us to the conclusion that q is 68.716049 times 10 to the minus 6 coulombs, which is approximately 6.9 times 10 to the minus 5 coulombs to two significant figures. We've rounded to two significant figures here because we are limited by the precision of the lowest precision piece of data given to us in the question. In this case, our data is to two significant figures, so therefore we can't be any more confident in our answer than to two significant figures either. Note that the fact that Q is bigger than the other charge, plus 46 microcoulombs, this is a good sanity check. Because P is further away from Q than it is from the plus 46 microcoulombs charge, we expect that Q must have a larger charge in order to repel more. Therefore, our answer looks sensible. In this question, we got 1 mark for making the statement that the magnitudes of the two fields had to be equal. We got 1 mark for rearranging to this expression here and substituting in the distances correctly, and we got 1 mark for calculating the correct value of Q, 6.9 times 10 to the minus 5 coulombs. The next part of the question says, explain, without calculation, whether net work must be done in moving a proton from infinity to position P, figure 2. So, just to draw a diagram that represents what's going on, we have that Q is putting out an electric field, and the 46 microcoulomb charge is putting out an electric field, and at position P here, the electric field strength is 0. However, just because the electric field strength is 0, it doesn't mean that the electric potential is also 0. The electric potential is not a vector quantity, it's a scalar. So what this means is that given that the equation for the electric potential of a charge Q is given by Q over 4 pi epsilon naught r, and it's a scalar, and both charges have the same sign, when I add their potentials together, this will give a number which is greater than 0. Now, the potential at a point, for example P, is defined as the work done to move a unit charge from infinity to that point. Therefore, if we're moving a proton from infinity to position P, what we can see is that because there is a potential that's greater than 0, then we have to do work on the proton, since the work done is given by the potential time multiplied by the size of the charge that the potential is acting upon. Note that this equation, W is equal to Q times V, implicitly assumes that the potential at infinity is zero. For a general change, we have to use the more general equation, W, the work done, is equal to Q multiplied by delta V, the potential difference. In this case, um, delta V is equal to V here, because the potential at infinity is zero, and delta V is V minus V at infinity. Therefore, our answer is that work must be done on the proton because the potential at P is positive, whereas the potential at infinity is zero. Therefore, there is a potential difference, and so work is done. Note that here we got 1 mark for saying that the potential at P is positive, and so work is done, and we got 1 mark for saying that the potential is zero at infinity. These two facts combined allow us to form the conclusion that work is done on the proton. The last part of the question says, a small rubber ball coated with conducting paint carries a positive charge. The ball is suspended in equilibrium from a vertical wall by an uncharged, non-conducting thread of negligible mass. The wall is positively charged and produces a horizontal uniform electric field perpendicular to the wall along the whole of its length. Figure 3 shows that the thread makes an angle of 30 degrees to the wall. The thread breaks. Explain the motion of the ball. Since we are considering electric fields and have been asked to explain the motion of the ball, it is helpful to consider the forces acting upon the ball as soon as the thread breaks. Specifically, we have the weight of the ball, and we have the electric field, or electric force. We can add these two forces together in a vector sum to give the following triangle, where that's the force from the weight, and then there's the force from the electric field. So the resultant force comes from adding these two together, tip to tail, like so, which we must do because they're vectors, and gives us a resultant force, which I'll call F. Since we've been asked to consider the motion of the ball, we now need to relate the resultant force F to the acceleration of the ball, as that will tell us about its motion. Therefore, the fact that we want to know about the motion implies we want the equation Newton's second law, F is equal to ma, provided that the mass of the ball is constant, which in this case it is. Since the acceleration is given by the resultant force divided by the mass, what we see then is that we have acceleration in the direction of the resultant force. Therefore, the ball accelerates in a straight line along this direction, which comes from the resultant force that I've described here. Since the ball had no initial velocity, the ball only accelerates in the direction that it has a resultant force in. Therefore, the motion of the ball is in a straight line. So our answer is that the ball experiences both horizontal and vertical forces, leading it to a resultant force, which gives it a constant acceleration and causes it to move in a straight line. In this question, we got 1 mark for saying that the ball experiences both horizontal and vertical forces, as described over here, and we get 1 mark for saying either that it has a constant acceleration or that it's caused to move in a straight line. This question is about capacitors. The question says, state what is meant by a capacitance of 370 microfarads. In order to answer this question, we need to know the definition of the capacitance, specifically that the capacitance is the charge stored per unit PD, where the PD is the potential difference across the capacitor. Whenever a question then asks you to explain a specific capacitance, in other words, a capacitance that has a specific value, in this case 370 microfarads, you need to relate it specifically to the units involved in this definition. Specifically, this means that 370 microcoulombs of charge could be stored for every 1 volt of potential difference across the capacitor. This is because the unit farad is defined as coulombs per volt, where coulombs is the unit of charge, volts is the unit of the potential difference. Therefore, our answer is that 370 microcoulombs of charge can be stored on this capacitor per unit volt of potential difference across the capacitor's plates. In this question, we got 1 mark for saying that we could store 370 microcoulombs of charge, and we got 1 mark for saying it's per unit volt. We have to use the units of the quantities here, since we've been given the capacitance that's in microfarads, rather than just defining what the capacitance is, in which case you wouldn't use units. The next part of the question says, the charging of a 370 microfarad capacitor is investigated using the circuit shown in figure 4. Both meters in the circuit are ideal. So in other words, the ammeter doesn't provide any resistance, and there's no current through the voltmeter. The power supply of EMF 9.8 volts has a negligible internal resistance. The capacitor is initially uncharged. When the switch is closed at time t is equal to 0, charge begins to flow through resistor R. The time constant of the charging circuit is 1.0 seconds. Calculate the resistance of R. In this question, since we've been given both the value of the capacitance of the capacitor and the time constant, it's helpful to consider an equation that relates the time constant to the resistance and the capacitance. Therefore, we can use the equation tau, the time constant, is equal to R times by C. Rearranging then, we have that R is equal to tau divided by C. So at this point we can substitute numbers in. Specifically, we know that we have 1.0 seconds as the time constant, and we know that the capacitance is 370 times by 10 to the minus 6, where this conversion here comes from converting microfarads to farads, because the micro is a prefix which includes a 10 to the minus 6. Doing that calculation then, we find that the resistance is approximately 2702, which to two significant figures is 2.7 times 10 to the 3. So this is 2.7 times 10 to the 3 ohms. We've rounded our answer to two significant figures here, because the precision of all the data in the question is to two significant figures, and whenever deciding on the precision of your answer, you should round to the same degree of precision as the lowest precision piece of data in the question, as otherwise you can't be any more confident about the degree of precision that your answer is given to. Next part of the question says, identify with the symbol X on figure 5 the potential difference across the capacitor when the switch has been closed for 2.0 seconds. And then they also want us to sketch the graph that shows how the potential difference varies from t equals 0 to t equals 2.0 seconds. In order to answer this question, we're interested in how the voltage of the across the capacitor changes over time. Therefore, we should use an equation that relates the voltage of the capacitor to the time elapsed since the switch has been closed. Specifically, we want the equation V is equal to V0 multiplied by 1 minus e to the minus t divided by RC, where e is Euler's number, which is approximately 2.718, and V0 is the potential difference across the capacitor as the time goes to infinity, in other words, whenever the capacitor is completely charged. Therefore, whenever the capacitor is completely charged, there's no current in the circuit, so all of the potential difference must be across the capacitor, because for a resistor, V is equal to IR, and if there's no current, there can be no voltage because the two are directly proportional. Therefore, since the EMF of the battery is 9.8 volts, we know that V0 has to be equal to 9.8 volts, because all of the voltage from the battery is across the capacitor. This is reflected in the equation because e to the minus t divided by RC for long times when the capacitor is nearly or fully charged will be equal to e to the minus a very big number, specifically because t is much bigger than the time constant. T divided by the time constant will be 5 or greater. Therefore, for these long times, we have the e to the minus big number is a very small number, so v is approximately v0. Then we can use the fact that RC is equal to the time constant tau, so we can rewrite this as v is equal to v naught 1 minus e to the minus t divided by tau. And then we can substitute numbers in. Specifically, at t is equal to 2.0 seconds, because that's the time we're interested in, we can write that v is equal to 9.8 multiplied by 1 minus e to the minus, and then we can use the fact that the time constant tau is 1 second. So we have that this is equal to 2 over 1, like so. So then, putting that into the calculator, we get a value of approximately 8.47 volts. Therefore, since the division between each voltage division on this graph is 2 volts, and this is nearly half a volt, we should be just less than a quarter of the way between 8.0 and 10.0 at time is equal to 2 seconds. So we want to be labeling x just about there. For the second part of this question, we need to use the fact that the capacitor charging follows a similar idea to exponential decay. Namely, that at first it's very easy to push charge onto the capacitor plates because there's no charge already on the plates to repel it. However, as more and more charge is added, it's harder and harder to push additional charge onto the plates because all the existing charge on the plates repels. Therefore, the rate at which charge is deposited onto the plates decreases with how much charge is actually sitting on the plates already. Therefore, we expect the voltage to increase fastest at the beginning of the charging process and to decrease as the time goes on, since it's harder and harder to put more charge onto the capacitor and thus to increase the voltage, since Q, the charge stored in the capacitor, is equal to CV, the definition we used earlier in the question. Therefore, our graph should look something like this. In this question, we got 1 mark for putting our cross X at the correct position, and we got 1 mark for our graph being correct. Note that we can't have the gradient of this graph being horizontal at 2 seconds, because this is only two time constants. Therefore, the capacitor won't have finished charging yet. And we can see that from our value of the voltage. It's 8.47 as opposed to 9.8, which would be the final voltage that we'd expect if the capacitor had pretty much finished charging. Therefore, a flat gradient here won't get you the mark. So 1 mark for the point and 1 mark for a correct graph. The next part of the question says, calculate the time taken for the charging current to fall to half its initial value. To answer this question, we need the equation for the half-life of the capacitor current, which is given as T half is equal to tau multiplied by the natural logarithm of 2. This equation isn't given on the datasheet, so I will quickly derive it now. The current follows the equation I is equal to I0 multiplied by e to the minus t over tau, where tau is the time constant like we said before. So this is the current I, and I0 is the initial current. So we can divide both sides by I0 to leave us with I divided by I0 is e to the minus t divided by tau. This I divided by I0 represents the half the initial value at the time we're interested in. So setting the time equal to the half-life and I divided by I0 to be a half, because that's what we're interested in this question, we would get the value a half is equal to e to the minus t half divided by tau. We can then take logarithms of both sides, So we take the natural logarithm, which gives us logarithm of a half is equal to the natural logarithm of e to the minus t half divided by tau. From there, we can use logarithm laws. So we can rewrite that natural logarithm of a half is equal to logarithm of 2 to the minus 1 using laws of indices. And then we can use the rule for logarithms, which says that you can bring the power down to the outside of the logarithm. Specifically, that the minus 1 can be brought out here, and the minus t half divided by tau can also be brought down. So you get something which looks like minus t half divided by tau natural logarithm of e is equal to minus the natural logarithm of 2. Now, the natural logarithm of e is equal to 1. Therefore, we have that t half divided by tau is equal to the natural logarithm of 2. So t half is equal to the time constant tau multiplied by natural logarithm of 2. This is the same equation as for radioactive decay, just with different symbols. Anyway, we can calculate this time now as a t half is equal to the time constant, which is 1.0 seconds, multiplied by the natural logarithm of 2. Doing this calculation, we find that this is approximately equal to 0.69 seconds. So our answer is 0.69 seconds. Here, I've rounded this to 2 significant figures because the degree of precision of the time constant, which is the only piece of data that we've used in this calculation, is also to 2 significant figures. The next part of the question says, calculate the time taken for the charge on the capacitor to reach 3.0 millicoulombs. In order to do this question, we need to use the equation for how the charge across the capacitor varies over time. Specifically, we need to use Q is equal to Q0 multiplied by 1 minus e to the minus t over tau, because the two are related by the equation Q is equal to CV, so the charge on the capacitor is just proportional to the voltage. Going from here then, we need to work out what the final charge on the capacitor will be. So that value is Q0. So to do that, we need to use the equation Q is CV, because we know what the final voltage is. It's 9.8 volts from the battery, like we commented earlier. So Q0 is equal to C times by V0. And then we have that C is equal to 370 times 10 to the minus 6, because it's 370 microfarads. And then V0 is 9.8 volts. So doing that, we calculate that Q0 is 3.626 times 10 to the minus 3 coulombs. Then we use the equation Q is equal to Q0 1 minus e to the minus t divided by tau, with tau being equal to 1.0 seconds. And here we want to rearrange for t. So we divide both sides by Q0, and then that leaves us with 1 minus e to the minus t divided by tau. We then subtract q divided by q0 from both sides, and add e to the minus t divided by tau to both sides, leaving us with e to the minus t divided by tau is equal to 1 minus q divided by q0. So finally, if we take logarithms of both sides, then we're left with natural logarithm of e to the minus t divided by tau, which is equal to natural logarithm of 1 minus q divided by q0. We can do the same trick that we did in the previous part of the question and bring the power down, like so, and also use the fact that natural logarithm of e is just equal to 1. So doing both of those steps at once, we have that this is equal to minus t divided by tau natural logarithm of 1 minus q divided by q0. So finally, we get that t is equal to minus tau multiplied by the natural logarithm of 1 minus q divided by q0. So now we have q, we have q0, and we have tau, so we can substitute these numbers in, and in doing so, you find that this is equal to minus 1.0 times by natural logarithm of 1 minus 3 times 10 to the minus 3 over 3.626 times 10 to the minus 3. So the 10 to the minus 3 from the milli prefix and the 10 to the minus 3 that we calculated from the final charge have cancelled each other here. Therefore, if we had anticipated that in advance, we could have just entered in 3 divided by 3.626 in order to save us time typing this in. So, doing that, we find that the answer is 1.75653 seconds, which to two significant figures is 1.8 seconds. And the reason we've rounded to two significant figures here is because the data given in the question, the lowest precision piece of data is to two significant figures. And in fact, all data in this question is to two significant figures. In this question, we got 1 mark for calculating the maximum charge on the capacitor, like so. We got 1 mark for substituting into the q is equal to q0 multiplied by 1 to the minus 1 minus e to the minus t divided by tau equation. And we got 1 mark for successfully rearranging that to get the right answer as 1.8 seconds. This question is about electromagnetic induction. The first part of the question says, state Lenz's law. Lenz's law says that in electromagnetic induction, the direction of the EMF produced is such that it opposes the change in the magnetic flux that produces it. Lenz's law is indirectly a statement of conservation of energy, because if the EMF produced favored the change that had produced it, then that change would continue to happen, and therefore more and more energy would be produced as more and more of an EMF would be produced. The next part of the question says, Lenz's law can be demonstrated using a bar magnet and a coil of wire connected to a sensitive ammeter, as shown in figure 6. The bar magnet is moved towards the coil and is then brought to a halt. State how the reading on the ammeter changes during this process. In order to answer this question, it is helpful to consider how the magnetic field that the coil experiences from the bar magnet changes as the bar magnet moves. Specifically, consider a point somewhere in the coil, and then consider the bar magnet outside of it. Then the field lines from the bar magnet when the bar magnet is far away will look something like this. For two example field lines. If the bar magnet is a bit closer, and we have something which looks more like the North Pole here and the South Pole here, so the field lines are closer together in that part of the coil. What this diagram conveys then is that the magnetic flux density is going to change as the bar magnet gets closer to the coil, because the magnetic field lines are closer together. Therefore, because we have a magnetic flux density that's changing, we can use Faraday's law. The induced EMF is equal to N, the number of turns in the coil, multiplied by delta phi divided by delta t, the rate of change of magnetic flux. Therefore, since phi is equal to BA times by cosine theta, where we don't need to worry too much about this definition in rigorous detail to answer this question, we can see that because B is changing, we'll experience an EMF being produced because this changes phi, which changes the magnetic. So the magnetic flux is changing. Because the magnetic flux is changing in a given time, there's the EMF. Now, because there is a complete circuit that the coil is connected to, This means that we also get a current. Therefore, while the bar magnet is moving, there is a changing magnetic flux density, and so an EMF and a current. When the bar magnet stops moving, the magnetic flux density that the coil experiences stops changing, so there should be no reading at that point because there's no longer a rate of change of magnetic flux. The next part of the question says, during the demonstration, an induced current is detected by the ammeter. The induced current is in the direction E to F. Explain how this demonstrates Lenz's law. To answer this question, it is helpful to consider the magnetic field that the coil will produce on the bar and see how this affects the bar magnet. This is because the bar magnet is a magnetic object, and so we expect it to feel a magnetic force from other magnetic fields. Therefore, if we know about the magnetic field of the coil, we can determine whether the motion of the bar magnet is opposed. So, drawing a diagram of the coil, we have something which looks like this, the ammeter there. And this is point E, and this is point F. So we have a current that's going this way through the coil, and because we have a current that's going like this, we know that for a coil of wire or solenoid, the magnetic field in this coil goes in the same direction as the current while inside the solenoid. So we get a magnetic field that looks like this, because the magnetic field of a solenoid is similar to that of a bar magnet. So therefore, this is our magnetic field. Since we know that this is like a bar magnet, we can see that there is a north pole produced at the right-hand side of the coil, because this is where the magnetic field lines are pointing from, and there's a south pole on the left-hand side, because this is where the magnetic field lines are pointing to. Therefore, we see that the coil behaves like a bar magnet, with the north pole facing the north pole of the actual bar magnet. Therefore, because we have two north poles here, and each one is going to be putting out a magnetic field that wants to make a north pole move away from it, what that means is that these two north poles repel each other. Therefore, the motion of the bar magnet is opposed because it is being repelled away from going where it is being made to move. So our answer is that the current produces a magnetic field in the coil, which is a north pole at the right-hand side of the coil. This opposes the motion of the bar magnet since the two north poles repel each other. In this question, we get 1 mark for saying that the current has produced a north pole on the coil's right-hand side. We get 1 mark for either saying that this opposes the motion of the bar magnet, or for saying that the two north poles repel each other. The next part of the question says, Figure 7 shows an arrangement for investigating induced EMF. As shown, the uniform vertical magnetic field is confined to the gap between the poles of the magnet. The plane of the square coil is horizontal and is made of conducting wire. The coil consists of a single turn and is attached by a flexible wire to an oscilloscope. The oscilloscope gives a reading of 2.9 times 10 to the minus 4 volts when the coil is moved at uniform speed from position G outside the field to position H inside the field, as shown in figure 8. We're told that the length of the side of the square coil is 32 millimeters, and we're told that the magnetic flux density of the uniform magnetic field is 0.38 teslas. Calculate the time taken to move the coil from position G to position H. Since in the question we're told that there's an EMF induced across the ends of the coil, and we want to know the time taken for this process to happen, it makes sense to consider Faraday's law, which contains both of these variables. Therefore, we can write epsilon, the magnitude of the EMF, is equal to n, the number of turns in the coil, multiplied by delta phi divided by delta t. This fraction represents the rate of change of magnetic flux, where the magnetic flux through the coil is given by the magnitude of the magnetic flux density multiplied by the area that magnetic flux density moves through, multiplied by cosine of theta, where theta is the angle between the normal to the area and the magnetic flux density. Consider the normal to the area of the coil. So this is the normal here. And then we have our magnetic flux density coming downwards, like so. And say in this case that it's off at some angle to the initial, to the normal. This is what the angle theta represents. So here we're viewing the coil side on. Therefore, what we see is that this angle theta appears in the magnetic flux equation. Since we're told that the coil is moved at uniform speed into the magnetic flux density, what we can say is that delta phi divided by delta t is equal to a constant, because the change in magnetic flux is happening at a constant rate. Therefore, we can see that this has to be equal to the magnetic flux at the end, subtracting the magnetic flux at the start. This is the change in the magnetic flux divided by the change in the time, which we'll just call t, and that's the quantity we're interested in knowing. Now, using the definition of the magnetic flux, we know that the magnetic flux at the start is equal to 0 multiplied by the area of the coil. This is because there's no magnetic flux density out here. Whereas at the end, it's going to be equal to the magnetic flux density B multiplied by A multiplied by cosine of 0 degrees, because this is the angle between the normal to the coil and the magnetic flux density. Since cosine of 0 degrees is 1, this is just equal to BA. The area of the coil, since it is a square, is just given by 32 millimeters all squared. So doing that, that's 32 times 10 to the minus 3 all squared. Then we can rearrange our equation for epsilon to make t the subject. So using that phi start is equal to 0, we keep phi end, and we divide by t, and then we use the fact that n is equal to 1. So I won't include it further. Therefore, we can say that t is equal to phi end divided by epsilon. So from there, we can put in the numbers for phi end and for epsilon. Specifically, the phi end is b times a. So this is 0.38 multiplied by the area, which is 32 times 10 to the minus 3. Remember, this 10 to the minus 3 comes from the fact that we've got millimeters here. So what that means is, because milli corresponds to a power of 10 to the minus 3, we need to include that. And then we divide by the size of the EMF, which is 2.9 times 10 to the minus 4. Therefore, we're left with a time of 1.341793103 ... which is approximately equal to 1.3 seconds to two significant figures. And here we've rounded to two significant figures because this is the degree of precision to which the data in the question is given, and we're limited by the precision of this data. In this question, we got 1 mark for trying to use Faraday's law and rearranging it, and we get 1 mark for a correct final answer. The last part of the question says, the square coil is rotated through 360 degrees at a constant angular speed about the horizontal axis as shown in figure 9. Calculate the angular speed of the coil when the maximum reading on the oscilloscope is 5.1 millivolts. In order to answer this question, we need the equation for the EMF induced in a rotating coil, specifically that EMF is given by the angular speed, omega, multiplied by the magnetic flux density B, multiplied by the area of the coil A, multiplied by the number of turns in the coil N, multiplied by sine of omega times by t, where t is the time elapsed. So we already know a few things from this equation. Specifically, we know what n is, that's equal to 1. We know that a is going to be equal to 32 times 10 to the minus 3 all squared, so that's from the previous part of the question, and we've been told that b is equal to 0.38 teslas. The sine omega t in this equation comes from the fact that at different times, the rate of change of the area that the magnetic flux density is moving through is changing. Specifically, the omega t just represents the total angle that the coil has rotated through. Consider the coil at the initial time when it's just started moving. The two dotted lines at the edge of the flat line, which represents the coil, denote how much of the area is exposed to the magnetic flux density. Now consider it when it's rotated through 45 degrees. In this case, we can see that now less of the area is exposed to the magnetic flux density. And consider it again after 90 degrees, a 90-degree rotation of the coil. In this case, none of the area is exposed. Therefore, it's changing fastest whenever we move between 45 degrees and 90 degrees, as opposed to between 0 degrees and 45 degrees, where it hasn't changed very much. So in this case, we have a maximum rate of change of the cross-sectional area, and therefore a maximum rate of change of the magnetic flux at 90 degrees. Therefore, we can just use the value of sine when it's at 90 degrees, and this corresponds to the maximum of the sine, so that makes sense. Therefore, we say that we want to pick sine omega t is equal to sine of 90 degrees, which is equal to 1. Therefore, we can just use the equation epsilon is equal to omega ba, where I've set n equal to 1 here. And I've removed the sine because we now know that we're looking at it when sine is equal, when the angle inside the sine omega t is equal to 90 degrees. Therefore, we can rearrange this for omega to give omega is equal to epsilon divided by ba. Then substituting in the value of epsilon, which is 5.1 times 10 to the minus 3, which comes from converting millivolts to volts. And then we divide by 0.38 multiplied by the size of the area, which is 32 times 10 to the minus 3, all squared, for the same reasons as before. Therefore, we get that omega is equal to 13.1064967 which is approximately equal to 13 radians per second. Therefore, our answer is 13 radians per second to two significant figures. In this question, we got 1 mark for using epsilon is omega ba times by n, and we've used n as 1 here. So knowing that the maximum EMF comes whenever sine of omega t is equal to 1. And then we got our 2nd mark for a correct final answer. This question is about radiation. The first part of the question says, suggest with a reason which type of radiation is likely to be the most appropriate for the sterilization of metallic surgical instruments. In order to answer this question, we need to consider the 3 different kinds of radiation, specifically alpha, beta, and gamma. So the idea is that gamma is the most penetrating of these 3. This means that it is most likely to fully sterilize the instruments. This means that it is most likely to fully sterilize the instrument, since there's the most chance that the radiation passes all the way through a given instrument and therefore sterilizes the entire surface. Therefore, our answer is gamma, because it is the most penetrating. Note that the mark for this question was for the reason, as well as the choice of gamma, not just the choice of gamma. The next part of the question says, explain why the public need not worry that irradiated surgical instruments become radioactive once sterilized. In order to examine the answer to this question, we need to understand what happens for something to become radioactive. Specifically, the nucleus, which will contain the protons and neutrons of the metallic instruments, must be changed. So radiation must be absorbed. And this radiation must be absorbed in such a way that it causes the nucleus to become unstable. Therefore, what would happen is that then the nucleus would decay. And this denotes at this point, when the nucleus is unstable and ready to decay, this means that it has become radioactive. So therefore, our radiation needs to be absorbed by the nucleus in order for it to become radioactive. However, ionizing radiation has the property that it affects the outer electrons in the atom rather than the nucleus itself. Therefore, it could not be absorbed by the nucleus. As a result, there is no chance of the nucleus becoming radioactive, and thus there is no need to worry about this possibility. Therefore, our answer is that ionizing radiation does not affect the nucleus. The next part of the question says, a student detects the counts from a radioactive source using a GM radiation detector, as shown in figure 10. So we have our source separated from the GM detector by a distance d. The student measures the count rate for 3 different distances d. Table 1 shows the count rate in counts per minute, corrected for background for each of these distances. Explain, with the aid of suitable calculations, why the data in Table 1 are not consistent with an inverse square law. You may use the blank columns for your working. In order to answer this question, we need to understand what an inverse square law is. Specifically, we can say that the intensity of radiation is equal to a constant divided by the distance from the source, d, all squared, which means that it's proportional to 1 over d squared. This defines the inverse square law. Therefore, if this follows an inverse square law, it would mean that the intensity, I, multiplied by d squared, would be equal to the constant k, which is the same for all 3 of the measurements. If this constant k is not the same for all 3 measurements, then it means that we have not followed an inverse square law. In this case, the intensity of the radiation, I, is proportional to the count rate. Because if I have more counts, then it means that I'm receiving more radiation in a given time, which means that I have a higher intensity of that radiation. Therefore, our strategy will be to calculate I multiplied by d squared, and then see what value of k we get. So doing that, in the table we can calculate the correct count rate, which I'll call c, multiplied by d squared, and that's in units of counts per minute times meters, all squared. So doing that, we find that this is equal to 9013 times 0.2 squared for the first one, 1395 multiplied by 0.5 squared for the second one, and 242 times 1 squared for the third one. This will give us a value of c times d squared is equal to k as 360.52 for the first measurement, as 348.75 for the second measurement, and 242 for the third measurement, and that's again in counts per minute times meters squared. Therefore, since the values of k aren't the same, it means that this data does not obey an inverse square law. Therefore, our answer is For an inverse square law, c multiplied by d squared should be a constant. However, here c multiplied by d squared is not a constant, so this data does not obey an inverse square law. In this question, we got 1 mark for our conclusion, which is based on the fact that c times d squared should be constant, and we get 1 mark for forming this conclusion from calculating c times d squared for 3 data points, like so. The last part of the question says, state 2 possible reasons why the results do not follow the expected inverse square law. In order to answer this question, we need to consider possible problems with the source that would lead to us not getting the intended behavior. There are several different reasons that this could be, but for 2 that are directly related to the behavior of the source, we have that for 1, we may have different types of radiation. For example, say we had both beta and gamma radiation in this case. Gamma radiation has a very long range, whereas beta would be attenuated before you got to the 1 meter mark, which is the final measurement in this case. So therefore, if this is not a pure gamma source, but instead also contains beta emitters, then the count rate that you get closer to the source will be much larger due to the presence of those beta particles compared to, let's say, 1 meter. Therefore, you don't get an inverse square law in this case, since only the gamma radiation follows an inverse square law, whereas the beta radiation does not follow an inverse square law. Another possible reason is found by considering the behavior of the source. Specifically, think about how radioactive the source is. This comes from A is equal to lambda n, where A is the activity and n is the number of radioactive nuclei. The point being that here, if the number of radioactive nuclei changes while the measurements are being taken, then the activity will be affected, and this will in turn affect the count rate. Therefore, in order for these measurements to give us an inverse square law relationship, we need the number of radioactive nuclei to remain about the same throughout the entire experiment. If it decreases significantly, then our count rate will be affected. So this will only happen if we have a short half-life. Because if we have a short half-life, like on the order of minutes, while this experiment is being performed, then the activity will decay quite quickly on the timescales that we care about. And as a result, we'll have a lower count rate. Because of that, the count rate will appear to decrease, even if the distance between the detector and the source is maintained as the same. Things will get even worse if the detector is moved further away, because then you'll have the contribution from the inverse square law, as well as the fact that some of the nuclei have decayed, so the activity has decreased. Keep in mind that this only really matters if the number of radioactive nuclei changes dramatically. In the experiment, some will be decaying anyway, but as long as this is a small number relative to the total number in the sample, the activity will remain roughly the same. Therefore, our reasons are 1. That the source is not a pure gamma emitter, and the second reason is that if the emitter has a short half-life, then the count rate will decrease due to radioactive decay. In this question, we got 1 mark for each correct reason. This question is about radioactive decay. The question says, Figure 11 shows how radioactive decay of one nuclide can be modelled by draining water through a tap from a cylindrical tube. And here we see a diagram of the tube and the water. The water flow rate is proportional to the pressure of the water. The pressure of the water is proportional to the depth of the water. Therefore, the rate at which the depth decreases is proportional to the depth of the water. Before the tap is opened, the depth is 16.0 centimeters. The tap is opened and the depth is measured at regular intervals. These data are plotted on the graph in Figure 12. And so in Figure 12, we see an exponentially decreasing depth of water as a function of time. The first part of the question says, Determine the predicted depth of water when the time is 57 seconds. In this question, we're told that the depth of the water is proportional to the rate of change of the depth of the water, which is the defining property of exponential decay. This is why we can compare this process to the decay of a sample of a nuclide. So in this case, D corresponds to the depth of the water. So in the same way that we have an exponential decay equation for the number of nuclei, we can do the exact same thing for D as equal to Z0 e to the minus lambda t. Now, because we're interested in determining the predicted depth of the water when the time is 57 seconds, we're going to need to work out this decay constant lambda, or work out another quantity that's related to it that's easy for us to observe. Specifically, the easiest quantity like it that we want to observe is the half-life, because this is just the time taken for the depth of the water to decay by a half. Therefore, it's convenient to rewrite this equation as d0, the initial depth of the water, multiplied by half to the power of t divided by t half. So in order to proceed, we need to figure out the half-life. Specifically, we're looking for the time taken for the depth of water to halve. We can read this off from the graph by considering the initial depth, d0, as 16.0 centimeters, and then we look for the time at which this is halved, which is approximately 19 seconds. So approximately equal to 19.0 seconds. So our half-life, t half, is approximately equal to 19 seconds. Therefore, we can use the fact that d, the depth of the water at any given time, is equal to d0, which will be 16.0 centimeters, multiplied by a half to the power of the time, which is 57 seconds, in this case, divided by the half-life, which is 19. So here we've used that t half is about 19.0 seconds. This is 16.0 multiplied by a half to the power of 57 divided by 19, which is 3. So this will give us that d is equal to 2.0 centimeters. Therefore, our answer is 2.0 centimeters, where we've given our answer to two significant figures. The next part of the question says, suggest how the apparatus in figure 11 may be changed to represent a radioactive sample of the same nuclide with a greater number of nuclei. So, as we identified above, the decay of the depth of the water is given by the equation d is equal to d0 multiplied by half to the power of t, the time, divided by t half. So t divided by the half-life. So here, we see that this is an exponential decay, because we were able to relate this to another exponential decay equation above. Now, because of this, we see that if we just want to have a greater number of nuclei, which is related to this equation in a similar way, so the analogous equation for nuclei is given by n is equal to n0, a half to the t divided by t half, in the same way as before. So we can see that n0, the initial number of nuclei that are radioactive, is analogous to d0, the initial height of the initial depth of the water. Therefore, we need to increase the depth of the water to represent an increased number of nuclei. Therefore, our answer is to increase the depth of the water. The next part of the question says, suggest how the apparatus in figure 11 may be changed to represent a radioactive sample of a nuclide with a smaller decay constant. In order to answer this question, we need to consider the properties of an exponential decay, specifically that the time rate of change of the depth of water is going to be equal to minus lambda multiplied by d. This is similar to the equation for activity, which defines the rate of change of the depth of the water. So we can see that the depth of the water is, as discussed in the previous part of the question, is going to affect the number of nuclei in the sample, because that's analogous, The other properties that we're interested in are how quickly that decay occurs for a given size of the sample. And all that information is contained within lambda. So lambda affects the rate of decay. So therefore, we want any factor that slows down the rate at which the depth decreases. Therefore, we want to limit the flow of water. Looking back at our apparatus then, we see there are several different things we could say that would slow down the rate of water. For example, having the tap more closed, but not completely closed, will slow how fast the water goes through the tube. Also, for a given height, if we have a wider tube, or like so, then it means that more water has to leave the tube for each height, because the tube itself is wider, so there's more water at each height. We could also change the amount of water that can go through this capillary tube that connects the cylindrical tube to the tap, and that would also slow the rate of decrease of the depth. So any of these answers would be sufficient. And in this case, we're going to say that we want to use a wider cylindrical tube. The next part of the question says, the age of the moon has been estimated from rock samples containing rubidium and strontium brought back from moon landings. 8737 rubidium decays to 8738 strontium with a radioactive decay constant of 1.42 times 10 to the minus 11 per year. Calculate in years the half-life of 8737 rubidium. In order to do this question, we need an equation which relates the half-life, T half, to the decay constant, and this is given by T half is equal to 1 over lambda multiplied by the natural logarithm of 2. Therefore, in order to calculate T half, we can substitute into this equation directly, and we can use the decay constant is 1.42 times 10 to the minus 11, and then multiply that by the natural logarithm of 2. This gives us 4.88131873 times 10 to the 10, which is approximately 4.88 times 10 to the 10 years. Therefore, our answer is 4.88 times 10 to the 10 years to three significant figures. We've chosen three significant figures because the data given in the question is also supplied to three significant figures, and we're limited by the precision of this data. Note here that we didn't need to convert the units from years into seconds or anything like that, because we've been asked to give our answer for the half-life in years. Later on, we'll see that we need to do some conversions to get things in seconds. The next part of the question says, a sample of moon rock contains 1.23 milligrams of 8737 rubidium. Calculate the mass in grams of 8737 rubidium that the rock sample contained when it was formed 4.47 times 10 to the 9 years ago, and give your answer to an appropriate number of significant figures. In order to answer this question, we should use what we know about radioactive decay, namely that it is an exponential decay. Therefore, we can use the equation that describes how the number of radioactive nuclei in the sample changes, specifically that the number of radioactive nuclei at time t is equal to the initial number of radioactive nuclei, n0, multiplied by e to the minus lambda t, where lambda is the decay constant and t is the time taken. So, in order to go further with this then, we need to relate this to the mass of the moon rock, since that's the quantity that we've been given in the question. To do this, we note that the number of particles, n, is equal to the total mass divided by the mass of one nuclide. Therefore, we see that n, the number of nuclei, is proportional to m, the mass of all the nuclei. Therefore, we can rewrite this equation in a new form using the mass. Specifically, the mass at some time t is equal to the initial radioactive mass multiplied by e to the minus lambda t, in the same way as before. So, m0 is the initial mass of radioactive nuclides. And m is the current mass of radioactive nuclides. Okay, so from here then, we need to rearrange this equation in order to get the value of m0, since that's what we're interested in. We want to know the mass of radioactive H737 rubidium that was present when the rock sample was formed. Therefore, we can write, using m is m0 e to the minus lambda t, we can rearrange this as m0 is equal to m times by e to the minus lambda t, or e to the plus lambda t rather. Then we'll need to substitute numbers in for this, so we'll need the value of lambda, which we were provided with earlier in the question, as 1.42 times 10 to the minus 11 per year. Therefore, what we can say is that we have m0, substituting in, is equal to 1.23 times 10 to the minus 3. Now this comes from converting milligrams to grams, because we've been asked to write our answer in grams and not kilograms, as would be traditional for the maths, multiplied by e to the decay constant, 1.42 times 10 to the minus 11, multiplied by the time that we've been given in years as 4.47 times 10 to the 9. So note that we didn't have to convert any units up here because the decay constant is in units of per year and the time is in units of years. Therefore, the two units cancel out, so we're fine. And this gives us a value of 1.310604091 times 10 to the minus 3, which is approximately equal to 1.31 times 10 to the minus 3 grams. And this is to three significant figures. Our choice of three significant figures here is because the question has said that we need to give our answer to an appropriate number of significant figures. And when it asks you to do this, you should always give your answer to the number of significant figures of the least precise piece of data given to you in the question. This is because your precision for your answer is limited by how confident you are in the data you've been given to calculate it. Therefore, if one of your pieces of data was, say, to one significant figure, then that's the most confident you could be about your answer as well. So therefore, you would only give your answer to one significant figure. Here, all pieces of data have been given to three significant figures, so this is the precision that you can write your answer with. In this question, we got 1 mark for a correct calculation of lambda times by t up here. We got a mark for our correct final answer of 1.31 times 10 to the minus 3, and we got a mark for rounding to three significant figures, as explained. The last part of the question says, calculate the activity of a sample of 8737 rubidium of mass 1.23 milligrams, and give an appropriate unit for your answer. In order to answer this question, since we've been asked to calculate the activity of the sample, we should use the definition of activity, specifically that the activity is equal to lambda multiplied by n, where lambda is the decay constant that we've been given earlier in the question as 1.42 times 10 to the minus 11 per year, and n is the number of nuclei. So in order to calculate the activity, we'll need the number of nuclei. So to do that, we need to use the fact that n, the number of nuclei, is equal to the mass of the sample divided by the mass of one nuclei. So the reason for this is if I multiply the number of particles by the mass of one nuclei, then I should get the mass of the whole sample. So therefore, n is the number of radioactive nuclei. So first, we calculate n. So n is equal to 1.23 times by 10 to the minus 6 here. So this is converting milligrams to kilograms now. So we get a 10 to the minus 3 from converting milligrams to grams, and we get another 10 to the minus 3 from converting grams to kilograms, divided by the mass of one nuclei. So in order to calculate this, we need the proton mass, which is 1.673 times 10 to the minus 27 kilograms. So the reason that we converted to kilograms up here is because these units for the proton mass and the neutron mass, which we're going to use in a second, are also all in kilograms, and we want those units to cancel. So that multiplied by the number of protons in the sample, which is 37. So this is proton mass, number of protons, added to the neutron mass, 1.675 times 10 to the minus 27, and that will also be in kilograms, multiplied by the number of neutrons. So this is 87 minus 37, which is 50. So this is the neutron mass times the number of neutrons. So doing that calculation then, we find that n is equal to 8.44348 times 10 to the 18. So that's the number of radioactive nuclei in the sample. Next, we want to calculate the activity, and activity is traditionally given in per second. Therefore, this is the unit that we want to calculate the activity in. However, we have a problem. Lambda is per year. So need to convert to per second. So doing that then, we can change the unit on lambda by saying, well, if there's that many decays per year, then we need to divide by the amount of time in a year to get it into seconds. So specifically, we're dividing by the number of seconds in a year. So lambda has to be equal to 1.42 times by 10 to the minus 11 divided by the number of days in a year multiplied by the number of hours in a day multiplied by the number of minutes in an hour multiplied by the number of seconds in a minute. So this conversion takes us from years to days, from days to hours, from hours to minutes, and from minutes to seconds. So the overall conversion here is from years to seconds. So doing that calculation then, we find that lambda is equal to 4.50279 times 10 to the minus 19. Therefore, the activity A is given by A is equal to 8.44348 times 10 to the 18 multiplied by lambda 4.50279 times 10 to the minus 19, and altogether that gives us 3.8019222121 per second. So therefore, our answer to 3 significant figures, since that's the precision of the data given to us in the question, is 3.80. Now, a good unit for this would be per second, but there is another unit for activity 2, which is exactly the same as per second, but just has a different name. And so that unit that you could use is the becquerel, which has the symbol BQ, and they both represent the same thing. In this question, we got 1 mark for our correct answer for n. We got 1 mark for our correct answer for the activity, and we got 1 mark for our choice of unit as either per second or becquerel. This question is about radioactive decay. The question says, a nucleus of polonium, PO, may decay to the stable isotope of lead 208.82 Pb through a chain of emissions following the sequence alpha beta minus alpha. Figure 13 shows the position of the isotope 208.82 Pb on a grid of neutron number n against proton number z. The first part of the question then says, draw 4 arrows on figure 13 to show the sequence of changes to n and z that occur as the polonium nucleus is transformed into 282 Pb. In order to answer this question, we need to know what alpha and beta minus decay do to the proton and neutron numbers of the nucleus. So in alpha decay, what we have is that we lose 2 neutrons, and we lose 2 protons as well, because in alpha decay, alpha particle is given out. which is made up of 2 neutrons and 2 protons. Whereas in beta decay, what you have is that the actual nucleon number of the nucleus doesn't change, but instead, because a beta minus particle is given out, an electron, and charge is conserved, it means that one of the neutral charges in the nucleus, the neutron, must become a proton. So we have +1 to the proton number, and then -1 neutron, because one of the neutrons has turned into a proton. Therefore, on the diagram, an alpha particle being released will look something like this, since the proton number must decrease by 2, and also the neutron number must decrease by 2. Also, for a beta minus decay, we have that the number of protons must increase by 1, and then the number of neutrons must decrease by 1, so the overall arrow looks like this for a beta. Therefore, we need to follow the sequence of steps backwards in the directions given. Specifically, we have alpha, beta minus alpha, so we need to go back in the same sequence. So, in order to reverse one alpha decay, we need to go up by 2 protons and 2 neutrons. So we'll go like this. Then the nucleus we had before we did a beta decay, so like that. Since this removes a proton and gains a neutron, we would need to do the same again for the second loss of a proton and gain of a neutron. And then finally, we need to go back to the nucleus we had before we did the initial alpha decay, like so. So therefore, the arrows should look something like this, where this comes from the alpha, this comes from a beta minus, this comes from a beta minus, and this comes from an alpha. In this question, we got 1 mark for a correct representation of alpha and beta minus decay on the NZ diagram, like we've done here. And we got 1 mark for a fully correct decay chain. In other words, we start at the right place and all the arrows are in the right position. The next part of the question says, a nucleus of the stable isotope 20882 Pb has more neutrons than protons. Explain why there is this imbalance between proton and neutron numbers by referring to the forces that operate within the nucleus. Your explanation should include the range of the forces and which particles are affected by the forces. In answering this question, we should use what we know about the forces that operate within the nucleus. Specifically, the 2 forces that we must consider are electromagnetism and the strong nuclear force. Electromagnetism is a long-range force that affects charged particles, and therefore the only particles in the nucleus that will be affected are the protons, since there are only protons and neutrons present in the nucleus and neutrons are neutral. The protons repel each other. By comparison, the strong nuclear force is repulsive below about 0.8 femtometers and is attractive beyond this distance up to about 3 femtometers, after which there is no interaction between the nucleons. Thus, in the nucleus, what we see is that there is a balance between the 2 forces. Specifically, because all the protons are positive, they'll repel each other, and then the nucleons will attract each other through the strong nuclear force. Therefore, as the nucleus will try to pull itself apart more strongly due to the electromagnetic force between all the positive protons, which repel each other, having fewer protons reduces the electromagnetic repulsion between them. In this question, we got a maximum of 3 marks for talking about the nature of the various forces. Specifically, we would get 1 mark for saying that the electromagnetic force is long-ranged. We would get 1 mark for saying that it acts between protons to repel them. We get 1 mark for saying that the strong nuclear force affects all the nucleons. We would get 1 mark for saying that it is repulsive up to about 0.8 femtometers and attractive from 0.8 femtometers to 3 femtometers. And so overall, we would get 3 marks from that set of statements. Finally, we would get 1 mark for explaining the imbalance between the proton and neutron numbers, which is to say that we're reducing the electromagnetic repulsion between the positively charged protons. The next part of the question says, many, but not all isotopes of lead are stable. For example, 205-82 lead decays by electron capture to become an isotope of thallium, Tl. Write the equation to represent this decay, including the isotope of thallium produced. In order to answer this question, we need to use what we know about electron capture. Specifically, in electron capture, the electron is absorbed by the nucleus. This causes a proton to become a neutron by absorbing the electron. So therefore, we're looking to do something where we have an electron with a charge of -1 and a mass number of 0, plus the lead nucleus, 205-82 Pb, and we're looking to form something with the same mass number, because mass is conserved. So we have that the mass number should still be 205 here, and that we should have thallium, because this is what we produced, with a lowered proton number. Specifically, we have 81. Now, because lepton number is also conserved, and we have an electron on the left-hand side, which has a lepton number of 1, then we must also have a lepton number of 1 on the right-hand side. Then this means that we have to have an electron neutrino, like so, since an electron neutrino has a lepton number of +1. And because the mass is conserved, and we already know that the thallium still has a mass of 205, it means that the electron neutrino must have a mass of 0, and also the neutrino is uncharged, so it also has a charge of 0. This ensures that mass is conserved, lepton number is conserved, since we have the same number of leptons on the left and right hand side of the equation, and also that charge is conserved, since -1 plus 82 is equal to 81 plus 0. The next part of the question says, the thallium nucleus is formed in an excited state. Electromagnetic radiation is emitted from the thallium atom following its formation. Explain the origin and location of the two sources of this radiation. In order to answer this question, we need to understand the possible sources of this radiation. Specifically, first consider the excited nuclear state. If we go from the excited state to the ground state, then some energy is lost, and that energy is given off as a gamma ray. So therefore, that's going to be one source of our radiation. Also, consider what happens in electron capture, since we know that we're dealing with electron capture as the process through which the nucleus changes. Specifically, one of the inner electrons is absorbed by the nucleus, and then we get a new nucleus. Therefore, if this happens, then there's going to be a vacant spot where that electron should be. Therefore, an electron in an outer energy level will fall down to fill the gap, and as it falls down, it will emit energy, which again will be as radiation. Therefore, our answer is for the first point that the nucleus de-excites from an excited state to the ground state, releasing energy as a gamma photon. For the second point, we have that an outer electron in the thallium atom falls down to fill the empty gap in the inner energy level caused by electron capture, which also emits radiation. In this question, we got 1 mark for each correct point. The last part of the question says, other nuclides also emit electromagnetic radiation. Explain why the metastable form of the isotope technetium 9943 Tc is a radioactive source suitable for use in medical diagnosis. In order to answer this question, we need to list some relevant properties of 9943 technetium in its excited state that would make it useful in medical diagnosis. Some points could be that it has a half-life of only about 7 hours, which means that it exists in the body long enough for a diagnosis to be performed, but short enough that it doesn't exist in the body for very long. We can also use that it's a gamma emitter only, which means that it doesn't produce the very ionizing alpha or beta radiation, and also this means that the gamma radiation can leave the body and be detected, allowing the position of the technetium to be determined. This allows it to be used as a medical tracer. In this question, we get up to 2 marks for any 2 valid points. For example, having a long enough lifetime for the diagnosis to be performed, having a short enough lifetime that it doesn't stay in the body for a long time, that it's only a gamma emitter, and that it's weakly ionizing, or that it can be used as a tracer, as detailed here. This question is about ideal gases. The question says, the graph shows the variation of pressure P with temperature θ for a fixed mass of an ideal gas at constant volume. What is the gradient of the graph? In order to answer this question, we need to use the fact that we're dealing with an ideal gas at constant volume. Because we're dealing with an ideal gas, it means we can use the ideal gas equation, which says that PV is related to N, the number of particles in the gas, times by Boltzmann's constant, times by the temperature, which in this case is given by θ. So P over here is the pressure and V is the volume. Now, in order to find the gradient, we need 2 points. And what we're going to do is we're going to use the definition of the gradient, which is that the gradient is delta P divided by delta θ. So if I have 2 points that are denoted by θ1 and θ2 and P1 and P2, so for example, we might call this point here 120, or rather 20 and 100. So 20 is the temperature in degrees Celsius and 100 is the pressure in pascals. This would correspond to P2 and θ2. Now we have a problem because we don't know what our other point is going to be, and that's where the ideal gas law comes in. So specifically, because V is constant, and we know that we have a fixed mass of gas, so N is constant, as if we have a fixed mass, it means that we must have the same number of particles. Then what we're dealing with is PV is equal to NKB θ, and the only 2 things that are changing are P and θ. So we can actually deduce a second point on this graph. And specifically, we can deduce the point where P is equal to 0. We can find this by extrapolating this graph. So if I were to extend the temperature axis like so, then I could continue to draw this line back towards the pressure is 0 point, which would be at some temperature in Celsius, which would be given by absolute 0. The reason that this is true is because at the pressure being 0, the temperature must also be 0, since in the ideal gas, P is proportional to θ, so if P is equal to 0, then θ is also equal to 0. Therefore, we can write out our expression using our 2 points like so. So θ1 is going to be given by minus 273 degrees in Celsius, and our pressure is going to be given by 0. So this is absolute 0, or 0 in Kelvin. So then, calculating the gradient, we find that delta P by delta θ is given by P2 minus P1, so that's 100 minus 0, divided by 20, temperature 2, minus temperature 1, which is minus 273. So putting those numbers in, we get 100 divided by 293, which is equal to 0.3412969 ... which is approximately 0.341. Therefore, the answer to this question is A. This question is about ideal gases. The question says, 2 flasks X and Y are filled with an ideal gas and are connected by a tube of negligible volume, compared to that of the flasks. The volume of X is twice the volume of Y. X is held at a temperature of 150 Kelvin, and Y is held at a temperature of 300 Kelvin. What is the ratio mass of gas in X to the mass of gas in Y? To answer this question, we need to use the fact that we're dealing with ideal gases and that they're connected by a tube of negligible volume. In order for this system to be in equilibrium, we consider the 2 tubes, the 2 vessels connected to each other by this tube. Then what we see is that for the systems to maintain the same properties that they currently have, the pressure in each vessel must be the same. So if this was X and this is Y, the reason for this is because if I had a higher pressure in one flask compared to the other, then what we would be dealing with is more collisions on the walls of one of those two containers. For example, take that the pressure would be larger in Y. If this was the case, then we would get more collisions on all of the walls of Y compared to all of the walls of X. However, Y is not a completely closed container because it also has this tube that connects it to X. So we would get some particles that go down the tube from Y towards X. The same thing would happen in X, but because the pressure is lower in X, we would expect to see fewer particles going from X to Y than from Y to X. Therefore, what we can say is that for these conditions to be maintained, the pressures have to be equal. Because we're using the ideal gas law, we can then write an ideal gas equation for each of X and Y. For example, if I denote all the quantities specific to the flask X with an X and all the ones specific to flask Y with a Y, then we can write down the ideal gas law like so. So in each case, we have a number of particles for X or Y, we have a temperature for X or Y, and we have a volume for X or Y. And we're provided various information about the volumes and the temperatures in the question. Because the pressures are the same, the fastest way to proceed is to divide the two equations by each other. Specifically, we can divide the equation for the ideal gas for X by the one for Y. So we have PVX divided by PVY is equal to NX KB TX divided by NY KB TY. Now, the pressures will cancel. Boltzmann's constant will cancel because it's just a constant. And then we're left with this being equal to NX TX divided by NY divided by TY. We're interested in the number of particles in each flask because that will be related to the mass. Therefore, we want to put Tx and Ty on the other side of the equation. So we can write Nx divided by Ny is equal to Vx over Vy times by Ty divided by Tx. From there, we can use what we're told in the question about how the temperatures and the volumes are related to each other, specifically that Vx is equal to 2 times Vy, and we also know that Ty is equal to 2 times Tx, because the temperature of X is 150 and the temperature of Y is 300. So putting those in, we have 2 Vy divided by Vy multiplied by 2 Tx divided by Tx. And then here we see that Vy and Tx cancel, because they're on both the top and the bottom of their respective fractions. So we see that the ratio of the number of particles in X to the number of particles in Y has to be 4. Now we need to relate the number of particles in each flask to the mass of the gas in each of those flasks. We can do that by noting that the number of particles is going to be equal to the mass of all particles divided by the mass of one particle. So I'll rewrite this as m being the total mass divided by m1 to denote the mass of one particle. Now, because X and Y are have the same kind of gas in them, which they don't state explicitly, but we're just told that it's filled with an ideal gas, so there would be no reason to assume that they're different gases, given that they say ideal gas singular. So we know that M1 is the same. So we can then rewrite our ratios, Nx divided by Ny, in terms of the masses, Mx and My. So to do that, we write that this is equal to M1 times by Nx divided by M1 times Ny, which is equal to Mx divided by My. And that's still equal to 4. So then, our answer has to be C, because the ratio of mass in flask X to flask Y is 4. And note that in doing this, I've just rearranged this equation to multiply both sides by M1 to leave M1 times by N is equal to M. And then I've just given M appropriate subscripts for each flask here. This question is about mean square speed. The question says, the average mass of an air molecule is 4.8 times 10 to the minus 26 kilograms. What is the mean square speed of an air molecule at 750 Kelvin? In order to answer this question, since we're dealing with mean square speed and have been given the mass, it is helpful to consider the equation that relates the mean square speed to the temperature, the other variable we've been given. Specifically, we can write that a half multiplied by m multiplied by c squared bar is equal to 3 over 2 times by Boltzmann's constant multiplied by T, the temperature. So m here is the mass of an air molecule, and c squared bar is the mean square speed of the molecule. And that's what we're interested in finding. So from there, what we can do is we can rearrange this equation for c squared bar. We multiply both sides by 2 and divide both sides by m. So that gives us the equation c squared bar is equal to 3 kBT divided by m. We can then put in numbers. Specifically, what this looks like is 3 times 1.38 times 10 to the minus 23. So that's Boltzmann's constant. The temperature is 750 Kelvin, and the mass is given by 4.8 times 10 to the minus 26. So doing that, what we find is that c squared bar is equal to 646,875, which is approximately equal to 6.5 times 10 to the 5 meters squared per second squared. Therefore, our answer is C. This question is about Brownian motion. The question says, a transparent illuminated box contains small smoke particles and air. The smoke particles are observed to move randomly when viewed through a microscope. What is the cause of this observation of Brownian motion? In this experiment, the motion of the smoke particles comes from their collision with air molecules. Specifically, if I have a large smoke particle, and I have several much smaller air molecules that are all around it, then through the random motion of the air molecules, which we know happens in a gas, we have that they'll collide with the smoke particle, come off. Since they collide with the smoke particle, what's going to happen is that their momentum has to change. And because there's a change in momentum over a time, it means that a force is exerted on the particles. Through Newton's third law, that also means that there is a force exerted on the smoke particle. What that means is that this smoke particle is constantly jiggled about. As a result, what you observe is the random motion that they talk about in this question. Therefore, the cause of this observation is collisions between the smoke particles and air molecules. This question is about momentum changes. The question says, the diagram shows a gas particle about to collide elastically with a wall. Which diagram shows the correct change in momentum, delta mv, that occurs during the collision? So, a few things to note based on the information we've been given. Firstly, that because this is an elastic collision, we know that kinetic energy is conserved. In combination, we know that because the particle doesn't change to become another particle in this collision, its mass must remain the same. Therefore, what we're really looking at here for a change in momentum is equal to the change in v multiplied by m, if we were just looking at how large it was. However, we need to do a bit more work in this case because we're dealing with momentum in terms of its direction as well as its magnitude. In order to make progress then, we need to write this as some kind of vector sum, or in this case actually a vector subtraction. Specifically, delta p is given by m multiplied by v2 minus v1, where we subtract these as vectors. One way to think about how we subtract these as vectors and form our triangle is going to be to consider adding two vectors. Specifically, we can take the minus sign into v1. What I mean by that is that if we go up over here, then we can write that this is v2 plus minus v1. And then we can apply all the rules that we normally use when adding vectors together, specifically that we add them tip to tail. So now we need to figure out what the new velocity looks like from this collision. So firstly, we better define our velocities, specifically that v1 is the initial velocity, and that's already written on the diagram. It's at an angle of theta to the horizontal, and v2 is the final velocity. Then to proceed, we need to note that the wall is at right angles to the normal to the wall, this dotted line here, which I can also draw another one of there. So what that means is that only the component that's perpendicular to the wall of the velocity is affected by the wall. So the velocity here has two components, an upwards component, which looks like this, and a sideways component, which looks like that. So let's now write down what we know about v1, specifically. If I want to think about it like a vector, I would draw it something that looked like that. Now as for v2, we need to figure out, using what we know about this being an elastic collision, what v2 will look like. Specifically, we can use the fact that the magnitude of the velocity is the same because kinetic energy is conserved and the mass of the particle is also the same, because this is the definition of kinetic energy, a half mv squared. So therefore, we know that v squared is going to be equal to the upwards velocity, the upwards component of v2 all squared, plus the sideways component. Now, the upwards component is unaffected, as we said earlier, so that just leaves the sideways component. But we know that the size of the sideways component, in terms of its magnitude, also has to be unchanged in order to give the same v squared at the end. Therefore, we know that the sideways component has to have the same size. Putting this all together then, if I were to denote arrows that talk about the upwards and sideways component, they would look like that, where this is at an angle theta and has a magnitude of v. Therefore, we can write this out like this. So therefore, if I want to write down v2, it's going to look like this. Now, our final step before we can add these two together is to write out minus v1 as a vector. And specifically, we just have to change the direction of the arrow. So this will look like this. So now we're going to calculate delta p as m v2 plus minus v1, like so. So this then is, if we add these two tip to tail, we have an angle theta here. So this comes from v2, which has a magnitude of mv, because the size of the magnitude of the velocity is v, and the mass of the particle is m, and p is equal to mv. And then this comes from minus v1, which also has an angle of theta there, and this also has a side length of mv, because the magnitude of the momentum is the same after as before. Therefore, we need to pick the diagram that best represents this vector sum, where this side will be delta mv. Examining the diagrams we have, we can see that overall, the only diagram that fits these specifications is B. Therefore, our answer is B. This question is about the gravitational force. The question says, the distance between the Sun and the Earth is 1.5 times 10 to the 11 meters. What is the gravitational force exerted on the Sun by the Earth? In order to answer this question, we need to use the equation that relates the gravitational force experienced by the bodies to the masses of those two bodies and the distance between them. Specifically, if I have two masses, m1 and m2, they're separated by a distance r, the gravitational force, the magnitude of the gravitational force rather, can be written as F is equal to big G, which is Newton's gravitational constant, multiplied by m1 multiplied by m2 divided by r squared. In this case, it may look like we're a bit stuck since we haven't been given the masses of the Earth or of the Sun. Luckily, m1 and m2, where m1 I'm just going to choose to be the Sun and m2 I'm going to choose to be the Earth, are given on the datasheet. So we can take these values from the datasheet and use them in our calculation. The mass of the Sun is about 1.99 times 10 to the 30 kilograms, and the mass of the Earth is about 5.97 times 10 to the 24 kilograms. Plugging those values and the distance that we've been given into the equation for the force, we do the calculation as F is equal to 6.67 times 10 to the minus 11 multiplied by 1.99 times 10 to the 30 multiplied by 5.97 times 10 to the 24. And that's all over 1.5 times 10 to the 11, all squared. Putting those numbers in, we obtain that F is equal to 3.521848933 times 10 to the 22, which is approximately equal to 3.5 times 10 to the 22 newtons to two significant figures. Therefore, the answer to this question is A. This question is about gravitational potential. The question says, the graph shows how the gravitational potential varies with the distance between two planets, K and L, that have the same radius. Which statement is correct? A, the mass of L is greater than the mass of K. B, the gravitational field strength at the surface of L is greater than that at the surface of K. C, the escape velocity from planet L is greater than that from planet K. And D, more work must be done to move a mass of 1 kilogram from the surface of K to a distant point than 1 kilogram from the surface of L. In order to do this question, we need the definition of the gravitational potential, specifically that the gravitational potential is given by minus gm divided by r, where m is the mass of the body that's generating the potential, and r is the distance away from the center of that body. This represents the gravitational potential energy per unit mass to move an object from a distant point to that point in the gravitational field. We can see that it's negative, and this represents the fact that the gravitational force is attractive, so you're always going to get energy out as you move an object from infinity to the surface of a planet, say, because they're attracted together. You don't need to put in energy to perform this process. So, using this definition, we can compare some of the statements we've been given. So, based on the statements we've been given, we can see that a deeper gravitational potential well corresponds to more work being done to move a mass 1 kilogram from the surface of K, i.e. we need to get out of this well, and it's deeper than moving from the surface of L. So our answer would be D, but let's quickly discuss why the other answers don't work. Since we have our definition that V is minus gm divided by r on the surface of the planet, we can compare the heights of the gravitational potentials at the surface of K and L. For A, it says the mass of L is greater than the mass of K. Since they have the same radius, this can't be true, because this means that the only thing that's changing in the expression for the potential is the mass of the planet, and this would imply that L should have a deeper well than K, because it's massively bigger than K, and V is directly proportional to m, the mass of the planet. So A is out. For B, we have that the gravitational field strength at the surface of L is greater than that at the surface of K. Now, this is a little bit more subtle, but it comes from the gradient of the graph at K or L. Specifically, steeper gradient implies larger magnitude of gravitational field. This is an analogy to electrical fields, where you have the potential and the electric field is the gradient of the potential. In the same way, the gravitational field is the gradient of the gravitational potential. So here we can see that this is steeper. So what that means is that we have a larger field here. So steeper than the gravitational potential at L. So this has a smaller field. Therefore, B is out. For C, the escape velocity from planet L is greater than that from planet K. Well, using our knowledge that D is now the correct answer, the escape velocity is directly related to how much energy you have to put in, or how much work you have to do to escape from the surface of the planet. Since we know that we have to do more work to get off the surface of K and go to infinity than to go from the surface of L to infinity, we know that we must also require a larger escape velocity to get off K than to get off L. Therefore, C must also be incorrect. Therefore, we have no choice but to conclude that D must be the correct answer. This question is about potentials. The question says, the diagram shows equipotential lines near a group of asteroids. And we see regions of decreasing potential, and X is at the region with the highest potential, i.e. the highest gravitational potential energy. The question says, which arrow shows the direction of the gravitational field at X? In order to answer this question, we need to use two facts. First, we need to use the fact that the field is perpendicular to an equipotential at any given point. This is because the field is given in the direction of the maximum change of the potential. That's how it's defined. This is because the equipotentials represent directions along which the potential energy is not changing. The potential energy is not changing because the field can do no work along these lines, as otherwise the potential energy would be changing. So therefore, the direction in which the potential energy changes the most is perpendicular to the direction in which it does not change at all. So specifically, at x, if I want to change the potential energy the most, I need to move perpendicular to this equipotential. So that's our first fact. For our second fact, we need to consider whether direction is going to be right or left, as this now excludes A and B. I'm sorry, just so you can see the fourth answer is D to the right. So in order to understand this, we need to think about what direction a mass would move in this gravitational field. Specifically, our mass wants to move to regions of lower potential energy. This is because the field is doing work on that mass. So if we were just to leave the mass and then let the field act upon it, the field will automatically convert gravitational potential energy to kinetic energy of the mass, and in the process, it will lose more gravitational potential energy, lowering it. So in other words, the gravitational potential energy of a mass at x will be lowered as the field moves it away from x. Therefore, what we can see is that it wants to move towards the region with lower gravitational potential energy, which is denoted by all the subsequent equipotentials. So it would want to move towards them, and a rough trajectory would look something like this. So in this case, because the equipotential at x is directly vertical, it would want to move directly horizontal and to the left. Therefore, our answer is C. As motion in this direction fulfills the criteria that the field, which will produce a force in the same direction as the direction the field is pointing, to be perpendicular to the equipotential, and also moves the mass towards regions of lower potential energy. This question is about the gravitational potential. The question says, planet N has a gravitational potential minus V at its surface. Planet M has double the density and double the radius of planet N. Both planets are spherical and have uniform density. What is the gravitational potential at the surface of planet M in terms of that of planet N? In order to answer this question, we need to use the definition of the gravitational potential. So I'm going to write this just as potential, since the symbol V is already in use, and that's equal to minus gm divided by r at the surface of planet N. We now need to rewrite this using our expression for the mass of a spherical object in terms of its density. Specifically, we can use the equation rho, the density of the object, is equal to its mass divided by its volume. Then, because we're interested in getting rid of the mass and writing it in terms of the radius, which we've been told, we can rewrite this as m is rho v, and v, and I've noticed that I've drawn this as curly v here rather than a straight v because we're dealing with the volume, and I don't want to confuse that with the gravitational potential, and that's equal to 4/3 pi r cubed. So therefore, the mass of a spherical object with radius r is given by the density multiplied by 4/3 pi r cubed. Substituting this into our equation for the potential, we have that this is minus g divided by r times by 4/3 pi r cubed rho, which, tidying things up a bit, is given by minus 4/3 pi g r squared rho. Now we want to write this in terms of the potential minus v for planet N. So we say that N has a radius of r and a density of rho, whereas M has a density of 2 rho because it's got double the density of planet N, and it's also got a radius of 2r because it's got double the radius too. So if we write the potential that we figured out before for N, then that's going to be equal to minus v, like we're told in the question. As for M, we can use the same equation but substitute the quantities that we have for M in. So for M, we have that it's minus 4/3 pi g. We substitute in 2r squared, and we substitute in 2 rho because we're writing the quantities for M in terms of the quantities we have for N in order to get the potential at the surface of M, which is what we're interested in. So we obtain minus 4/3 pi g r squared again times rho, and this time we have 3 factors of 2, so that's equal to a multiplication by 8. So this is minus 8v. Therefore, we've shown that the answer has to be B. This question is about gravitational potential energy. The question says,
A spacecraft of mass 1.0 times 10 to the 6 kilograms is in orbit around the Sun at a radius of 1.1 times 10 to the 11 meters. The spacecraft moves into a new orbit of radius 2.5 times 10 to the 11 meters around the Sun. What is the total change in gravitational potential energy of the spacecraft? In order to answer this question, we need the definition of gravitational potential energy, since that's what we're being asked to calculate. This is given by EP, the potential energy, is equal to minus G, Newton's gravitational constant, m1, the mass of one of the objects, times by m2, the mass of the other object, divided by r, the distance between the centers of the two objects, m1 and m2. So it corresponds to this diagram here. Now, this has given us the potential energy that is present due to having two objects separated by this distance r. So from there, what we can do is we can calculate the change in potential energy by considering where the spacecraft is in each of its orbits. So, drawing a diagram, if we say that the spacecraft is orbiting the Sun and it's first at r1, and then later it's at r2, then what we can say is that because r1 and r2 are different, there has to be a change in the potential energy. So the potential energy in the first situation is just given by G times by m1, mass of Saturn, where we'll take m1 to be the mass of the Sun, and we'll take m2 to be the mass of the satellite, or spacecraft, rather. So we have G m1 m2 divided by r1, and then EP2 is the same, with the second radius in the place of the first radius. So calculating the change in the potential energy then, we can do delta EP, so using delta as the symbol for a change, as EP2 minus EP1, which is equal to minus G m1 m2 divided by r2 minus G m1 m2 divided by r1. What this means is that we can factor out G m1 m2 and also a minus sign to get minus G m1 m2 1 over r1 r2 rather minus 1 over r1. From here, we can then put the numbers in for this calculation. So we can find that delta EP is equal to minus 6.67 times 10 to the minus 11 in the datasheet. For the mass of the Sun, we take that from the datasheet too, and that's 1.99 times 10 to the 30 kilograms. And then we multiply by 1 over R2. So R2 from the question is given by 2.5 times 10 to the 11, and R1 is given by 1.1 times 10 to the 11. So doing this calculation, we find that because the denominator of this fraction for R2 is 2.5 times 10 to the 11, and the denominator for this second fraction is 1.1 times 10 to the 11, when I subtract this one for R2 from this one for R1, then I should get a negative number because 2.5 is bigger than 1.1. So this is a smaller fraction than this one. So therefore, it cancels without minus sign because a minus sign times a minus sign is a positive sign. So our answer will be positive. And then actually performing the calculation, we get 6.757316 ... times 10 to the 14, which is approximately equal to 6.76 times 10 to the 14 joules. And that's the three significant figures that I've rounded. So that means that it's in line with answer D. This question is about Kepler's third law. The question says, which graph shows the relationship between the time period t and the orbital radius r of a planet in orbit around the Sun? In order to answer this question, we need to use what we know about circular orbits and also about the gravitational force. So firstly, because we're in a circular orbit, we know that the centripetal force acting on the planet, F, is equal to mv squared divided by r, where m is the mass of the planet. So that's little m. V is its velocity and r is the radius of the orbit. We also know that for two objects that experience a gravitational attraction, the gravitational force has a size given by F is equal to little m, the mass of the planet, times by big M, the mass of the Sun, divided by r squared and multiplied by g. So g is Newton's gravitational constant and r is the radius of the orbit. Combining these two together, we get that mv squared divided by r is equal to m times big M times g divided by r squared, which then gets us the relationship that v squared is equal to mg divided by r, since one of the r's cancels and the little m's cancel. So we're left with big M here. To proceed, we need to use the fact that we're undergoing circular motion. And in circular motion, we can relate v to the radius of the circle by doing v is 2 pi r divided by t. And this also brings in the time period. This is why we choose this equation, because we want to get rid of v and rewrite it in terms of the time period. So this equation is just speed is distance over time for a circle. So bringing that in then, we have 2 pi all squared times r squared divided by t squared is equal to mg divided by r. So rearranging one more time, we find that t squared is equal to 4 pi squared divided by gm multiplied by r cubed. Now we can use this to examine which of the graphs are correct. If we first get it in terms of t, so make t the subject of this equation, we can figure out whether a or d are correct. So if we take the square root of both sides of this equation, we find that t is equal to the square root of 4 pi squared divided by gm multiplied by r to the 3 over 2. This shows that t has to be proportional to r to the 3 over 2, so a and d are out, because in a, t is directly proportional to r to the 2/3, and this one is out because t is proportional or directly proportional to the logarithm of r here. So that's no good. If we take logarithms of both sides, then we can determine which of c or b has to be the correct answer. Taking the logarithm of the left, we just get log t. Taking the logarithm of the right, we get log of this constant, square root 4 pi squared divided by gm, multiplied by r to the 3 over 2. We can then use a log law to separate out this log. So what we're doing is we're using the fact that the logarithm of a product of two terms is equal to the sum of the logarithms of the two terms individually. So this becomes log 4 pi squared divided by gm, all square rooted, and then the log is taken, and then log of r to the 3 over 2. We can then use another log law, which says that for a number which is held to a power within a log, you can take the power and put it out front. And this is just a logarithm law. So from there, we can write log t is equal to 3 over 2 times by log of r plus log of square root 4 pi squared divided by gm. So here, what we see is a straight line relationship between log t and log r. This is consistent with c, and so c is the correct answer. This question is about gravitational fields and density. The question says, the Earth can be assumed to be a uniform sphere of radius r. What is the mean density of the Earth? In order to answer this question, we should look at the form of the answers. Specifically, we're told that the answer contains little g, the value of the gravitational acceleration. So what this means is that we probably want to use the formula for the size of g. So the size of g is given by gm divided by r squared on the surface of the Earth. Since we're looking to find the density of the Earth, what we should do is we should try and get the density into this equation so we can relate g to rho being the density. So to do that, we use the equation for the density, rho is equal to m divided by v, and then we rearrange to get m is rho v, where v is the volume of the Earth. So then we use the fact that we're dealing with a uniform sphere of radius r. And that tells us that v is equal to 4/3 pi r cubed. So m is equal to rho times by 4/3 pi r cubed. We can then substitute that in and get g is equal to big G divided by r squared times by rho times 4/3 pi r cubed, like so. And so tidying up a bit, we find the r squared cancels with r cubed to leave just an r. So little g is equal to rho big G times 4/3 pi r. And so rearranging for the mean density, we find that rho is equal to free g divided by 4 big G. And then we also have pi r on the bottom. Therefore, because this is the same as answer A, we conclude that A is the answer. This question is about electric fields. The question says, a conducting sphere holding a charge of plus 10 microcoulombs is placed centrally inside a second uncharged conducting sphere. Which diagram shows the electric field lines for the system? In order to answer this question, it is helpful to consider a diagram of the charges involved in this system. Specifically, if I have my central charge, or my charged sphere, which has a positive charge of plus 10 microcoulombs, and then I surround it with another conducting sphere, then I should consider what happens inside that conducting sphere. Specifically, what I mean by that is that originally, from the plus 10 microcoulomb charge, I'm going to have an electric field which comes outwards radially, which is what we know happens for a normal positive charge, provided it is a point charge. So in my conducting sphere that's on the outside, I have electrons which are free to move and ions which are not. So what happens then is that my electrons, upon seeing this this electric field that's pointing outwards, the electrons are attracted towards it. They're attracted to the positive charge in the center. So what happens is that electrons move from being uniformly dispersed throughout the conducting sphere to going towards the surface, for example, like this. What this means then is that, and I'm just going to represent the rest of them by minuses to avoid making it more complicated than it needs to be. So what that means is that I'm left with loads of positive ions on the outside of the conducting shell, which do not have any electrons to cancel out their charge. Note here that the reason for the positive charge accumulating on the outside is just because the electrons have moved away from there. There are still ions on the inside of the shell too, but there are more electrons than there are ions, so there's a net negative charge. So cleaning up this diagram a bit, we set up a system which looks a bit like positive charge, negative charges surrounding that positive charge in the second conducting sphere, and then on the outside of the second conducting sphere, I've accumulated a load of positive charge. So if I look outside of this conducting sphere, all I see is a load of positive charge on the outside. So that just looks like a point charge if I get further away. In other words, I would expect an electric field that comes off it that goes like this. And that's a radial field. As for the inward field, we know that the field lines go from positive to negative, so we would have field lines that look something like this. And then the same on the outside, which I can't draw all of. But what that means then is that immediately we can discount some of the possibilities which are wrong. So for example, A has electric field lines pointing towards the positive charge. That's just no good, and we could have considered that to not be correct from the beginning. For B, we see that the field lines terminate whenever they get outside of the second conductor. So that's no good either, because we know that due to the positive charge on the outside of the second conductor, we should still get electric field lines coming off. C corresponds to the situation we've drawn, so that will end up being our answer. And D has field lines coming into the second conducting shell, which is no good because there's positive charge on the outside of that shell. So what it means is that I'm left just with these field lines coming out rather than coming in. Therefore, our answer is C. This question is about potentials and conductors. The question says, a charged spherical conductor has a radius r. An electric field of strength E exists at the surface due to the charge. What is the potential of the spherical conductor? In this case, we've been given a number of answers which could determine how the electric field and the radius are related. In order to figure out which one is correct, it's helpful to consider another case where we know how the electric field and the potential are related. So a similar case is the parallel plate capacitor, or rather when I have two plates like this, and I set up an electric field between them. So that would be an electric field, a uniform electric field that is, of E, and the plates are separated by distance d. Then we know that the potential difference V is equal to E times D, or this comes from the equation E is equal to V divided by D. So what this means then is that we know the units of the potential, which are the same every time, are the units of the electric field times by the units of distance. Now, provided that the electric field contains more units than just the units of distance within it, specifically what I mean by that is that the units of the electric field are newtons per coulomb, which, if you express it as in its base units, contains kilograms and amps, as well as seconds, then what it means is that I can't possibly form, for example, E squared, because then that would contain kilograms squared. In fact, the base units of this are kilogram meter per second cubed per amp. So therefore, for example, if I squared E, then I would have kilograms squared, and there would be no way for me to turn that into kilograms again to satisfy the definition V is ED, which would just be kilogram meter squared per second to the minus 3 per amp. So what I'm saying is that by using dimensional analysis, we can consider which of these cases has to be correct. So A is out because it's got a distance squared times by E, so that wouldn't give the correct units. B, I've already discussed why that's incorrect. For C, it's got the electric field divided by a distance, so that won't give us the correct units for the potential either. Finally, that leaves us with D, which is also distance multiplied by electric field. And if you were to more comprehensively go through the units, what you would find in this case is that this satisfies the correct units for the potential and the rest do not. But we can take a bit of a shortcut using this method I've detailed here. So our answer is D. This question is about potentials. The question says, 4 positive charges are fixed at the corners of a square as shown. The total potential at the center of the square at a distance d from each charge is 5q divided by 4 pi epsilon naught d. What is the magnitude of the fourth charge? In order to answer this question, we should consider the expression for the potential of a point charge. So, potential of a point charge is given by V is equal to Q, for a point charge of charge Q that is, divided by 4 pi epsilon naught R, and R is distance from the point charge. The other fact we need is that the potentials add, and the potentials are scalar quantities rather than vector quantities, so it means we can add them directly. So, sum of potentials then is given by Q divided by 4 pi epsilon naught d, plus the same thing from the second charge, say. So this would be, if I label them, these all give an identical quantity, but we should just label so we know exactly where they're coming from. 1, 2, and then 3. And then finally, we have this unknown charge, which I'm going to call Q prime. So plus Q prime divided by 4 pi epsilon naught d. So this is 3, and this one here is from charge number 4, which is in this corner. Okay, and that's going to be equal to the value that they've given us in the question, 5q divided by 4 pi epsilon naught d. So tidying this up a bit, we see that we have 3q divided by 4 pi epsilon naught d plus q prime divided by 4 pi epsilon naught d is equal to 5q divided by 4 pi epsilon naught d. And we can multiply both sides by 4 pi epsilon naught d to simplify our equation. So we have that 3q plus q prime is equal to 5q. And by subtracting 3q from both sides, we find that q prime is equal to 2q. So, in other words, this matches answer D, so our answer is D. This question is about capacitors. The question says, an air-filled parallel plate capacitor is charged from a source of EMF. The electric field has a strength E between the plates. The capacitor is disconnected from the source of EMF, and the separation between the isolated plates is doubled. What is the final electric field between the plates? In order to answer this question, it is helpful to write the electric field in terms of quantities which don't change and the quantities that do change that we're interested in. So before we do that, we should consider the implications of the various steps presented in the question. Specifically, disconnecting the capacitor from the EMF and from the circuit means that the charge on the plates has nowhere to go if you move the plates. So it means that the charge on the plates is the same. So what we can say is that if we're using the equations Q is CV, for example, we know that Q must be constant. So now let's use our capacitor equations and use the fact that we're using a parallel plate capacitor. So capacitor implies that we can use the equation Q is equal to CV, and the fact that it's a parallel plate, so with the plate separated by some distance d, implies we can use the equation E, the electric field, is equal to V divided by D. So combining these two equations together, if I multiply the first one by D, the second one, if I multiply the second one, E equals V divided by D on both sides, then I get V is equal to ED. So I can write Q is equal to C ED. So we're nearly there, except that the capacitance is going to change whenever the separation between the plates is doubled. To take that into account, we need to use the equation for C for a parallel plate capacitor, which is that C is given by epsilon naught, epsilon R, which in this case epsilon R is 1, so I won't keep writing it, multiplied by the area of the plates divided by the distance between the plates. So what that means then is that Q is given by epsilon naught A divided by D multiplied by ED, which is equal to, tidying up, the D's cancel, like so, to leave us with epsilon naught A E. So simplifying, E is equal to Q divided by epsilon naught A. So what this means is that the field is independent of the separation of the plates. It doesn't appear anywhere in that equation. So what this means then is that even if I double the separation between the plates, it won't affect the electric field at all. Therefore, our answer has to be B. This question is about parallel plate capacitors. The question says, a parallel plate capacitor has square plates of length L, separated by distance D, and is filled with a dielectric. A second capacitor has square plates of length 2L, separated by distance 2D, and has air as its dielectric. Both capacitors have the same capacitance. What is the relative permittivity, epsilon R, of the dielectric in the first capacitor? In order to answer this question, we should use the equation which relates the capacitance of a parallel plate capacitor to its geometry. Specifically, let's see, for any parallel plate capacitor, the capacitance is given by epsilon naught, the permittivity of free space, multiplied by epsilon R, the relative permittivity, multiplied by the area of that capacitor plate, divided by the distance between the two plates, D. So in this case, we have, for capacitor 1, we have C1 is equal to epsilon naught, epsilon R, which will correspond to the dielectric and will be greater than 1, multiplied by A. And since it's a square, A is equal to L squared. So specifically, our area A is given by the area of this square, so L times L. So this is for 1, divided by the distance between the plates, which is D. So it corresponds to that situation where this has the area A. As for capacitor 2, we have C2 is equal to epsilon naught multiplied by 1. So here I've set epsilon R for the second capacitor equal to 1, which comes from the fact that there's an air gap between the two plates, whereas in 1 we have some kind of dielectric, which is usually a block of some kind, but I've just drawn it like that to resemble that there is something between the plates, multiplied by the area. So in this case, we have a situation where we've got 2L and 2L, so this area is going to be 2L all squared. And then the distance between the plates, this time, is given by 2D. So that's on the bottom using this equation. So setting the two equal to each other, we find that epsilon naught, epsilon R, L squared divided by D is equal to epsilon naught times by 2L all squared divided by 2D. So we cancel out common factors here. We can cancel out the L squared, we can cancel out the D. and we can cancel out epsilon naught. So what we're left with is epsilon r, the relative permittivity of the dielectric, is equal to 4 divided by 2, which is equal to 2. Therefore, our answer is C. This question is about charging of capacitors. The question says, the graph shows the variation of potential difference with charge for a capacitor while it is charging. And here we see a directly proportional relationship between the potential difference and the charge. Which statement can be deduced from the graph? So the fastest way to narrow down your options in this question is to note that we have potential difference on one axis and charge on another. So this graph says nothing about the time involved in this charging process. What this means then is that if we consider statements A or B, which says A, the charging current is constant, or B, the energy stored in the capacitor increases uniformly with time, both these statements refer to a time involved, because A is talking about the charging current, I is equal to Q divided by T, the charge flowing through past a point divided by the time in which it takes for that charge to flow past that point, and B explicitly references time. So these two are automatically out because they're talking about an explicit reference to time, which is no good because this graph tells us nothing about time. It just tells us about how the potential difference varies with the charge on the capacitor plates. As for C and D, we'll talk about D first, since that's the incorrect option. The reason that D is incorrect is because this is only telling us about the potential difference across the capacitor. It says nothing about the other components in the circuit. For example, I could have a more complicated circuit where I have a terminal PD and then I have some resistors in series with the capacitor. And in that case, we would have no way of knowing what was happening to the potential difference across the terminal because we could have variable resistors where we're changing the resistance as we do the experiment. Therefore, this rules out D and would leave C as our answer. Another route through, which would allow you to not consider the other options, is to consider the graph of PD against charge. Specifically, we can use that the capacitance C is equal to Q divided by V. So what we see then is that V is equal to Q divided by C. So V is directly proportional to Q, and the gradient, if that is plotted as a straight line graph, is 1 over C. So that implies that if the gradient is constant, it implies that C is constant, since 1 over C is also a constant. So that would be another way to reason that the answer is C. This question is about magnetic fields. The question says, different magnetic fields are present in two chambers shown. A particle enters the first chamber at a velocity of 80 meters per second and is deflected into a circular path of radius 200 millimeters. In the second chamber, it follows a circular path of radius 100 millimeters. The question then says, the particle leaves the second chamber at a speed of A, 20 meters per second, B, 40 meters per second, C, 80 meters per second, and D, 160 meters per second. So in order to answer this question, we could attempt to analyze the circular motion of the particle through the various chambers. However, there is a much faster way to solve this problem. Specifically, we know that the magnetic force is always at 90 degrees to the path of the particle, and therefore does no work, because there is no distance moved in the direction of the magnetic force. Therefore, the energy of the particle is unchanged. This means that it must have the same kinetic energy that it did whenever it first entered. Therefore, because it has the same kinetic energy at the start and the end, and the particle's mass hasn't changed, it means that the speed must also be unchanged. Since the kinetic energy is equal to a half times the mass times the speed squared, so if the kinetic energy and the mass are unchanged, it implies that the speed is also unchanged. Therefore, we can quickly conclude that the answer is C. This question is about magnetic fields. The question says, the diagram shows a clockwise current I in a circular coil placed in a uniform magnetic field B, with the plane of the coil perpendicular to the magnetic field. What is the effect on the coil of the interaction between the current and the magnetic field? And we're given a number of options. Since we're told that we're dealing with a current carrying wire in a magnetic field, it makes sense to consider the left-hand rule. Specifically, that if you imagine your thumb and first two fingers, and you align them all at 90 degrees to each other, so you have the thumb, the index finger, and you have coming out of the screen, in this case, this would refer to your second finger. These quantities represent the force that a current wire is carrying a current in the direction of the second finger would experience due to a magnetic flux density, or uniform magnetic field in this case, going in the direction of the index finger. Okay, so what we're going to do is we're going to apply this to various parts of the coil. So even though the coil is circular, we can still consider each individual part of it. If we zoom in far enough, it will look approximately straight. So if we do that, what we see is that, consider one which is going upwards. So this is the left-hand side of the coil. So we have the current going upwards like that. We have the magnetic flux density going into the page. So if we apply our left-hand rule, then what we see is we get a force which goes outwards to the left. If we look at a segment on the top where the current is going like this, then what we would see is we would experience the magnetic flux density again going into the page. And so because of that, what we experience is a force going upwards. Similarly, we can do the same game for the right-hand side and the bottom. And if you do that, with the magnetic flux density going into the page and the current going downwards, then we get a force going in the other direction, like this. And then for the bottom, we have a similar situation where we have I coming out, and I should label B on all of these, by the way, to denote the magnetic flux density. Then it means that we get a force going downwards. So the net effect is that every bit of the coil is being pushed outwards from where it currently is. So what that means then is that we should see an increase in the diameter of the coil due to the force acting on it. The other options correspond to rotations, which would be if the magnetic flux density was in the plane of the page, and you can verify that by using the left-hand rule. And for D, the force would have to be going inwards rather than outwards. So in that case, the current would have to be going in the other direction for that to make sense, which again you can verify with the left-hand rule. But anyway, our answer is C. This question is about transformers. The question says, a transformer has an efficiency of 80%. It has 7,000 turns on its primary coil and 175 turns on its secondary coil. When the primary of the transformer is connected to a 240 volt AC supply, the secondary current is 8.0 amps. What are the primary current and secondary voltage? In order to answer this question, it is helpful to consider conservation of energy. Specifically, we know that the power in should be the power out, taking into account efficiency. So in other words, the efficiency, E, times power in is power out. Therefore, since we're told that the efficiency is 80%, we can write 0.8 times by the power in, P in, is equal to the P out. Now we can use that the power in is given by the current in the primary multiplied by the voltage in the primary, and that the power out is similarly given by the current in the secondary multiplied by the voltage in the secondary. Putting these things together, we find that 0.8 times IP Vp is equal to Is Vs. So then we know in the question that we've been given the primary voltage as 240 volts, and we're told the secondary current. So we want to write this expression here in terms of things we know and related to the things that we've been given in the answer. Specifically, since we have the primary voltage and the secondary current, then what we can write is that the secondary voltage divided by the primary current, Vs divided by Ip, is equal to 0.8 multiplied by Vp divided by Is, which, if we put in the values that we know for Vp and Is, we have 240 divided by 8, which gives us 24. So our strategy is going to be to calculate Vs divided by Ip for each given value that we have for answers A to D and see which one matches 24. So I've just added 2 new columns to our table so we can do a bit of a comparison. So doing this, we find that for A, Vs divided by Ip is equal to 6 divided by 250 times 10 to the minus 3, where the 10 to the minus 3 comes from doing milliamps to amps, and which we'll use for the remaining answers, and this gives us 24. So A will be our answer. If you do this for B, C, and D, then you find 37.5, 38,400, and 60,000, respectively. So none of these are equal to 24. Therefore, our answer here has to be A. This question is about electron scattering. The question says, which graph shows how the intensity I varies with angle theta when electrons are diffracted by a nucleus? In order to answer this question, we need to use the two key concepts that are involved, specifically that we have diffraction of the electron beam, much like diffracting light for a single slit, and that the electrons are attracted to the nucleus due to the electric force. So discussing each of these effects, which I'll label 1 and 2, firstly we'll talk about 1, the diffraction. So what this diffraction does is it causes an interference pattern, much like shining light for a single slit. What this does is it causes there to be interference, and as a result you get a series of minima and maxima. I should say that these aren't directly analogous, and the most similar analogy is to a beam of light passing through a circular gap. Secondly, we have the attraction of electrons to the nucleus due to the electric force. So because the electrons form a beam of finite width, what it means is that some electrons will be closer to the nucleus than others as they go past. What that means then is that since the electric force depends on the distance between the two objects, in this case the nucleus and the electrons, the ones that go closer to the nucleus feel a stronger electric force and are attracted more. However, there will be less ones that are close to the nucleus compared to those farther away. Most of the electrons will be attracted a little bit, but the ones closer to the nucleus will be attracted a lot more. Therefore, what you see is that most of the electrons only have a small diffraction angle, with a few having large diffraction angles. So you get this combination of a decreasing amount of intensity and the intensity fringes. So looking at a diffraction pattern that fulfills all these criteria, we can examine A to D. So looking at B, C, and D, we all see that these have some features that match, but not all of them. So for example, in B, we have the fringes, but not the decreasing intensity. For C, we have one decreased intensity rather than the intensity decreasing on the whole. For D, we have no decreasing at all, but we do have the fringes and one wide fringe. So A is the only one that satisfies all these criteria that I've talked about. Therefore, the answer is A. This question is about the nuclear radius. The question says, the radius of a uranium-238-92 nucleus is 7.75 times 10 to the minus 15 meters. What is the radius of a 12-6 carbon nucleus? So in order to answer this question, we need to use the relation between the radius of a nucleus and the number of nucleons it has. Specifically, R is equal to R0, which is some reference radius, and which is usually about 1.2 femtometers. And then this A is to the power of a third. So A is the nucleon number here. Therefore, we can write this equation for both uranium and for carbon. Doing this, we have Ru is equal to R0, which is the same because it's just the same in every usage of that formula, whereas A is the thing that can change. So then we have A for the uranium nucleus, which is denoted by the subscript U. Similarly, we can do the same thing for the carbon nucleus. We can write that the radius of the carbon nucleus is R0 multiplied by the nucleon number of carbon to the power of a third. So at the moment we have a problem because we have two R0s and we haven't been given this information in the question and it's not supplied to us. However, what we can do then is, since it appears in both equations, we can just divide one by the other. The cleanest way to do this is to do RC divided by RU, because that means that we can multiply by RU in a second to get the value of RC. So what this does is, we do this division, we have AC on the top and AU on the bottom. And these two R0s cancel each other out, leaving AC divided by AU to the power of a third, where I've put these inside one set of brackets to make it easier to compute. Then we multiply both sides by Ru, which has been given to us in this question, giving us Rc is equal to Ru multiplied by Ac divided by Au to the power of a third. So putting those numbers in, we get 7.75 times 10 to the minus 15 multiplied by 12, remembering that for any element, the nucleon number is the one at the top, like so. So we've got 12 there divided by 238 to the power of a third. Now putting those numbers in, it gives us Rc is equal to 2.863 times 10 to the minus 15 meters, which is approximately equal to 2.86 to three significant figures, times 10 to the minus 15, sorry, to three significant figures, which gives us answer C. We've chosen three significant figures here because this is the degree of precision of data given in the question. So our answer is C. This question is about fission reactions. The question says, during a single fission event of uranium-235 in a nuclear reactor, the total mass lost is 0.23 times U. The reactor is 25% efficient. How many events per second are required to generate 900 megawatts of power? In order to answer this question, we're told, firstly, that we've lost some mass, and that we're looking for an energy output. Therefore, we should use that the energy released, E, is equal to that mass lost, m, multiplied by c squared, which is Einstein's equation. So, firstly, we know that the energy released from mass loss is given by E is equal to 0.23 times U times c squared. Now, we know that the useful energy is going to be the efficiency multiplied by this energy, because the rest of the energy is lost as heat. Therefore, we can say that this is 0.25, the efficiency, multiplied by E, the energy from one fission event. So then, if we know how much useful energy we get from one fission event, we need to multiply that by the total number of events we expect per second to get 900 megawatts of power. So, number of events is going to be given by n, so we can write 0.25 times n times E. And remember that this is per second, because we're interested in events per second, not just the number of events. And that's going to be equal to 900 megawatts. So then, we can rearrange this for n, and we can write that 900 multiplied by 10 to the 6, so mega gives us the prefix of 10 to the 6, divided by 0.25, multiplied by 0.23 times u times c squared is going to give us our answer. Substituting in numbers for this then, we have 9 times 10 to the 8, where I've just simplified that a bit, divided by 0.25 times 0.23 times by 1.661 times 10 to the minus 27 times 3 times 10 to the 8 all squared, which will give us our answer for n. So therefore, we have that n is equal to 1.04703 times 10 to the 20, which is approximately equal to 1.1 times 10 to the 20, which would mean that we match answer C. Therefore, our answer is C. This question is about nuclear reactors. The question says, which of the following substances can be used as a moderator in a nuclear reactor? In order to answer this question, we should recall the purpose of each one of these materials. Specifically, boron, as answer A, is used in the control rods. This is because it absorbs neutrons. Therefore, it would not be suitable for use as a moderator, because the role of the moderator is not to absorb neutrons, but to slow them down and absorb some of their kinetic energy. This slows them down to thermal speeds so that they could then take part in another fission reaction. For B, concrete is used for containment, specifically to shield the outside from radioactive material. For C, so uranium-238 is an alternative isotope to uranium-235, which is the kind used in nuclear reactors. On the whole, this is just a red herring. And finally, we have water. Water is used as a moderator in a nuclear reactor. This is because when fast-moving neutrons collide with water, it is good at reducing their kinetic energy without absorbing them. Strictly speaking, what actually happens is you have deuterated water, which is water with hydrogens that have 1 neutron and 1 proton in them, so an isotope of hydrogen, deuterium. This kind of water is much better at removing kinetic energy from the neutrons than normal water. Therefore, our answer is going to be D.